In 1972, NASA test-fired a nuclear engine in the Nevada desert that produced more thrust per kilogram of propellant than any chemical rocket ever built. It was called NERVA. Within the decade, Congress shut the program down, the test rig was disassembled, and the engineers who built it went home. We have never tested another nuclear rocket on American soil. Welcome to Space Cluster, where we trace the engineering the space age tried to forget. The rockets, America buried. The reactors that worked, the programs that died in filing cabinets, in committee rooms, in budget cuts approved by men who had never seen a turbopump fire. We strip away the press releases to show you the technical reality of what humans built when they tried to leave Earth. In this 4-hour documentary, you will trace the rise and fall of the American nuclear rocket, the NERVA, hot fires at Jackass Flats, the Soviet RD-0410 that quietly beat its American counterpart, the $1.4 billion engine NASA deliberately destroyed, the Mars missions cancelled by Richard Nixon, the 180-day Mars engine that would have put humans on the surface by the year 2000. Every chapter is grounded in declassified reactor data, primary engineering archives, and the specific budget decisions that left these rockets in storage.
In 1959, in a remote corner of California, American engineers detonated 6 explosive charges beneath a metal craft and watched it fly. Not crash, not tumble. Fly, controlled, stable, rising on a pillar of sequential explosions. They called it the hot rod test, and it proved something terrifying. Nuclear pulse propulsion actually worked. For decades, you've been told that nuclear rockets were just Cold War fever dreams, ideas too crazy to ever leave the drawing board. But that's not what happened. The real story is that America's brightest minds unlocked a technology so powerful it could carry impossible masses to the outer planets. And then, the world realized it had created something it couldn't control. This is the story of Project Orion, the spacecraft we successfully designed, tested in principle, and then buried forever. Not because it failed, but because it succeeded in ways that terrified us. The late 1950s were a time of profound frustration for anyone who dared to dream beyond Earth's atmosphere. Chemical rockets, the only game in town, were pathetically inefficient machines, barely capable of lifting their own fuel tanks into orbit, let alone carrying meaningful payloads to other worlds. Every kilogram of spacecraft required tons of propellant. Every mission to the moon was an exercise in extreme miniaturization and weight-saving desperation. Mars might as well have been in another galaxy. But at General Atomics, a team of physicists and engineers began sketching something audacious. What if, they asked? We stopped thinking of nuclear weapons as instruments of destruction and started seeing them as concentrated packets of energy. What if we could harness atomic explosions, not for war, but for propulsion? The concept was brutally simple. Detonate small nuclear charges behind a massive shock-absorbing plate and ride the explosions like cosmic surfing. Each detonation would deliver an enormous kick of momentum. String enough of them together, and you could accelerate a spacecraft to velocities that made chemical rockets look like toys. The efficiency difference wasn't incremental, it was revolutionary. Chemical rockets operate with a specific impulse, a measure of propulsive efficiency, of around 450 seconds. The best engines humanity had built could barely exceed that. Orion's nuclear pulse propulsion offered specific impulse values in the thousands of seconds, 6,000, even 10,000 seconds in some configurations. That's not twice as good. That's not 10 times better. That's a fundamental transformation in what's physically possible. To put it in perspective, the difference in efficiency between Orion and chemical rockets is roughly equivalent to the difference between a Formula One race car and a horse-drawn wagon, then multiplying that gap by another order of magnitude. What did this mean in practical terms? A conventional chemical rocket mission to Mars takes 8 to 9 months of continuous coasting through the void, exposing astronauts to cosmic radiation, bone loss, muscle atrophy, and psychological strain. Orion could make the same journey in 4 to 6 weeks. Not months, weeks. The outer solar system, Jupiter, Saturn, and beyond, would transform from destinations requiring decades of flight time to places reachable in months. And the payload capacity was staggering. While chemical rockets struggled to lift a few tons beyond Earth orbit, Orion designs contemplated carrying millions of pounds. Not a capsule with a handful of astronauts, a fully equipped colony, a battleship-sized vessel with laboratories, greenhouses, and living quarters. This wasn't theoretical fantasy confined to blackboards and academic papers. The team at General Atomics, led by some of the most brilliant minds in physics and engineering, worked through the mathematics with rigorous precision. Every calculation checked out. Every simulation confirmed the concept. And then they built a test vehicle. The Hot Rod was a small-scale demonstration craft, a metal cylinder designed to prove the fundamental principle. Instead of nuclear charges, they used conventional explosives, high explosives that could simulate the propulsive effect without the radioactive complications. In the summer of 1959, they took it to Point Loma and ran the test. 6 charges, 6 detonations. The craft rose on each explosion, stable and controlled, climbing higher with every blast. The physics worked, the shock absorption worked, the concept was validated. But to understand why this dream would ultimately become a nightmare, we need to meet the man who would become both Orion's greatest technical architect and its most haunted critic. Ted Taylor was a weapons designer, and by all accounts, one of the best America ever produced. His specialty was miniaturization, designing compact, efficient nuclear weapons that delivered maximum yield from minimum mass. In the world of nuclear weapons engineering, this was the highest form of art. Taylor could visualize chain reactions in his head, could intuitively grasp the complex physics of compression, fission, and energy release in ways that left his colleagues in awe. His designs were elegant, efficient, and terrifying. For Project Orion, Taylor was the perfect recruit. The propulsion system required small, efficient nuclear charges, essentially miniature bombs that could be mass-produced and deployed in rapid succession. Taylor's expertise in compact weapon design made him uniquely qualified to develop these pulse units. He threw himself into the work with characteristic intensity, seeing in Orion a chance to redirect his nuclear expertise towards something transcendent. Instead of designing weapons to destroy cities, he would design the engines to carry humanity to the stars. But Taylor's brilliance came with a troubling shadow. Years later, in a moment of painful honesty, he would describe the mindset that had driven him and his colleagues during those years of weapons development. He spoke of being captivated by technical sweetness, the seductive elegance of a perfectly designed nuclear device, the intellectual satisfaction of solving impossibly complex physics problems. In that state of captivity, he admitted, moral considerations faded into background noise. The human consequences of the weapons became abstractions, numbers on paper, theoretical blast radii on maps. He confessed to a particularly chilling memory. Sitting in a hospital waiting room while his wife was in labor, he found himself drawing circles on maps of Moscow, calculating the effects of his weapons designs, mapping out blast radii and casualty estimates. The juxtaposition was grotesque. New life about to enter the world in one room, while in another, he calculated how many lives his creations would end. The whole thing had gone out of control, he would later say, recognizing too late how completely the technical challenge had consumed him. This wasn't regret spoken in the moment. This was a realization that came much later, after years of enthusiastic weapons development, after the intoxication of technical achievement had worn off and left him staring at what he had actually built. And it was this same man, brilliant, obsessive, and morally compromised, who now turned his talents towards spacecraft propulsion. The very traits that made Taylor perfect for Orion were the same traits that should have served as a warning. His ability to abstract nuclear weapons into pure engineering problems, to see past the human cost to the elegant physics underneath, made him extraordinarily effective at his job. But it also meant he was precisely the kind of mind that could rationalize almost anything in service of technical achievement. Yet Orion needed more than weapons expertise. It needed someone who could take the raw concept and transform it into a viable engineering system, someone who could work through the brutal physics of riding nuclear explosions without being vaporized in the process. It needed Freeman Dyson. Dyson was a different breed of scientist, a Cambridge-trained theoretical physicist whose mathematical prowess was matched by a philosophical bent that constantly questioned the implications of the work. When he joined the Orion team, he brought not just technical skill, but a broader perspective, an ability to see beyond the immediate engineering challenge to the larger consequences. The core engineering problem was deceptively simple to state, but fiendishly difficult to solve. How do you survive being pushed by nuclear explosions? Each detonation releases energy equivalent to tons of TNT, creating a plasma fireball expanding at thousands of degrees and generating a shockwave that would instantly vaporize any conventional spacecraft. The Orion team's solution was the pusher plate, a massive shock-absorbing plate positioned at the rear of the spacecraft, designed to catch the expanding plasma and convert its energy into forward momentum. The pusher plate wasn't just a simple metal disc. It was a sophisticated ablative shield, coated with graphite grease that would vaporize in each explosion, carrying away the intense heat and protecting the underlying structure. With each detonation, a thin layer of coating would ablate away, sacrificing itself to keep the plate intact. The plate itself was designed to flex and absorb energy, spreading the impact across its entire surface. But absorbing the explosion was only half the problem. Each detonation delivered an instantaneous kick of 20 to 30 times Earth's gravity, enough to pulverize any human crew and shatter any equipment. The solution was a massive shock absorber system, essentially giant gas-filled pistons that would compress during each pulse, stretching the violent instantaneous acceleration into a more gradual push. These shock absorbers, some designs called for them to be the size of oil derricks, would smooth out those crushing 30G pulses into a manageable 2 to 3 Gs, comparable to what astronauts experience during a conventional rocket launch. The propulsion cycle would work like this. The spacecraft ejects a nuclear pulse unit, a small nuclear charge, from a magazine at the rear. The charge drifts backward, carried by a small propellant charge or spring mechanism. When it reaches the optimal distance, somewhere between 100 and 200 feet behind the craft, it detonates. The expanding plasma fireball strikes the pusher plate, delivering its momentum. The shock absorbers compress, absorbing and spreading out the acceleration. The spacecraft surges forward. The cycle repeats every few seconds. Pulse after pulse after pulse, riding a staircase of nuclear explosions into the cosmos. Dyson's calculations proved the concept was scalable. Small craft for orbital missions could use relatively modest pulse units. Massive interplanetary ships, true space cruisers, could use larger charges and achieve even higher performance. The physics worked at every scale, and the Point Loma test had demonstrated the fundamental principle with conventional explosives. Everything checked out. But as Dyson perfected the physics, as he refined the calculations and optimized the design, he began working through a different set of equations that would haunt him for the rest of his life. Each Orion launch wouldn't happen in a vacuum. It would happen in Earth's atmosphere, and each nuclear detonation would release radioactive particles, fission products that would be lofted into the stratosphere and distributed globally by atmospheric currents. This wasn't theoretical. This was inevitable physics. And Dyson, with his characteristic rigor, set out to calculate the cost. The numbers were grim. Each Orion launch, he calculated, would kill between 0.1 and 1 person worldwide from the resulting fallout. Not immediately, not in any traceable direct way. But statistically, inevitably, somewhere on Earth, someone would develop cancer from the additional radiation exposure. Someone's immune system would fail. Someone's cells would mutate in just the wrong way. The death would be anonymous, untraceable to any specific launch, but it would happen. For a single launch, the number seemed almost abstract. 0.1 to 1 person. A statistical ghost. But Orion wasn't designed for a single launch. A Mars mission might require multiple launches to assemble the spacecraft in orbit, to deliver supplies, to establish infrastructure. Each launch added to the body count. 10 launches, 20 launches. The numbers accumulated like a moral debt. Each mission to the stars purchased with anonymous deaths scattered across the globe. The team found themselves debating the unbearable. Is space exploration worth a handful of anonymous deaths? How do you weigh the advancement of human civilization, becoming a multi-planetary species, unlocking the solar system, ensuring humanity's long-term survival, against guaranteed casualties? The calculus was impossible because there was no common unit of measurement. How many statistical deaths equal the colonization of Mars? How much fallout is acceptable in exchange for reaching Jupiter's moons? Context made it worse. This was the early 1960s, and atmospheric nuclear testing was already ongoing. The United States and Soviet Union were detonating nuclear weapons in the atmosphere regularly, and scientists estimated this testing was already causing hundreds of additional cancer deaths annually worldwide. Orion would add to this burden. It wouldn't create the problem already existed, but it would make it worse. And unlike weapons testing, which both superpowers claimed was necessary for national security, Orion's deaths would be in service of exploration. Voluntary deaths. Chosen deaths. The team began to fracture philosophically. Some argued the cost was acceptable, even necessary. Humanity's future, they reasoned, lay beyond Earth. Every great exploration had come with risk and sacrifice. The deaths would be tragic, but justified by the magnitude of what would be achieved. Others, including Dyson, found themselves increasingly troubled. The technical sweetness that Taylor had described, that seductive elegance of a perfectly designed system, began to taste bitter. What good was reaching Mars if the journey required sacrificing people who would never know they'd been chosen? But before this moral debate could be resolved, before the team could reach any consensus on the acceptable cost of cosmic exploration, a different force was gathering, one that would render their philosophical struggles moot. The Pentagon had been watching Orion with great interest, but not for the reasons the scientists had hoped. Military planners looked at the designs and saw something very different from a Mars exploration vehicle. They saw a weapons platform, an orbital battleship, a nuclear-powered craft that could carry enormous payloads, withstand almost any attack, and loiter in space indefinitely. The same characteristics that made Orion perfect for exploration made it equally perfect for warfare. That massive payload capacity, loaded with nuclear warheads instead of habitats. That incredible durability, it could survive anti-satellite weapons that would destroy conventional spacecraft. That nuclear propulsion system, it meant the craft didn't need to return to Earth for refueling. It could stay in orbit for months or years, an unstoppable weapons platform circling overhead. Military strategists began sketching scenarios. Station an Orion craft in orbit loaded with nuclear weapons. It becomes an unassailable first strike platform, able to drop warheads on any target on Earth with minimal warning. Its pusher plate, designed to withstand nuclear explosions, would make it nearly invulnerable to defensive measures. Shooting it down would require multiple direct hits with nuclear-tipped interceptors. And even then, success wasn't guaranteed. It would be the ultimate high ground, the ultimate strategic advantage. Werner von Braun, the legendary rocket engineer who had dreamed of Mars since his childhood in Germany, fought desperately to keep Orion focused on peaceful exploration. Von Braun had spent his career navigating the uncomfortable intersection of rocketry and warfare. His V-2 rockets had rained down on London during World War II, and he'd spent the post-war years trying to redirect that technology towards space exploration. He saw in Orion a chance to finally, truly reach Mars, to achieve the dream that had driven him through decades of compromise and moral ambiguity. But von Braun was losing the battle. Military interest increasingly dominated the project's funding and direction. The Mars mission designs were still being developed, but they were becoming secondary to military applications, and international observers were horrified. The Soviets watched Orion's development with alarm, recognizing immediately that any American orbital weapons platform would force them to respond in kind. The arms race, already terrifying enough on Earth, would accelerate into space. The technology was irreducibly dual-use. There was no way to build a peaceful Orion spacecraft that couldn't also serve as a weapons platform. The same vessel that could carry colonists to Mars could carry warheads to Moscow. Every component, every capability served both purposes equally well. You couldn't have one without enabling the other. This was the geopolitical nightmare that the Orion team had inadvertently created. They had designed a technology so powerful, so versatile, that it threatened to destabilize the entire Cold War balance of power. Every nation would need one. Every superpower would feel compelled to deploy them. And space, the final frontier, the realm of peaceful exploration and scientific discovery, would become the ultimate battlefield. As international tensions mounted, as the Cuban Missile Crisis brought the world to the brink of nuclear war, political leaders faced an impossible choice. They could allow Orion to proceed, accepting the environmental cost and the military escalation, betting that the benefits of space exploration would outweigh the risks of weaponized space. Or they could find a way to stop it, to prevent the technology from ever being deployed, even if that meant closing the door on humanity's best near-term hope of reaching the outer solar system. In 1963, the choice was made. The Partial Test Ban Treaty prohibited all nuclear detonations in the atmosphere and in space. The treaty's intent was noble, but its language was a death sentence for Project Orion. The team made desperate pitches for workarounds, but the political will was gone. The world had decided the risks outweighed the rewards. Project Orion was officially canceled in 1965. The research was classified, the designs buried. For the team, the reactions were telling. Von Braun was devastated, his Mars dreams dead. Freeman Dyson was conflicted, morally relieved that the environmental cost would not be paid, but scientifically disappointed that such a powerful technology would be abandoned. The most capable spacecraft ever designed became a footnote in history. But the story doesn't end with cancellation. We are still living with the consequences. Modern missions to Mars still face a 9-month journey, exposing astronauts to immense risk from radiation and the hazards of deep space. But this wasn't inevitable. Orion, with technology that existed in the 1960s, could have made that trip in weeks. The solar system could have been open to exploration a generation ago. We had the key, and we chose to throw it away. We traded cosmic reach for earthly safety, a choice that forces us to confront an uncomfortable truth. Sometimes the most powerful technologies come with costs we cannot accept. The question that haunts Orion's legacy is whether we chose correctly. We had a path to reach Mars in weeks, to explore the outer planets within a lifetime. We proved it could work, and then we chose not to build it. Not because it failed, but because it succeeded too well, because the same fire that could carry us to the stars could also rain down from orbit, and because every launch would take its toll in anonymous deaths. Project Orion remains buried in classified archives, a monument to the road not taken. The designs could still be built, but we continue reaching for Mars with rockets that take 9 months instead of 6 weeks, accepting limitations we once knew how to overcome. Perhaps that was wisdom, or perhaps it was a failure of courage. But in that gap, between what we could do and what we decided we should do, lies one of the most profound questions humanity has ever faced. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
Picture this. You're standing at Cape Canaveral, watching humanity's most advanced rocket, a SpaceX Starship, thunder into the sky. Its 33 Raptor engines generate the power of 16 million horses. Yet this marvel of engineering will still take 9 agonizing months to deliver astronauts to Mars. Your great-grandchildren might live to see humans on Saturn's moons. Maybe. Now imagine standing at that same launch pad in 1965, watching a spacecraft the size of a battleship rise on pillars of atomic fire. Each explosion, a controlled nuclear detonation, hurls this 4,000-ton colossus higher, faster, until it's racing through space at velocities that make our best rockets look like horse-drawn carriages. Mars in 125 days. Jupiter in a year. The entire solar system opened within a human lifetime. This wasn't science fiction. This was Project Orion. Between 1958 and 1965, America's brightest minds at General Atomics, backed by the Air Force, DARPA, and NASA, designed, tested, and proved we could surf nuclear explosions to the stars. The mathematics were elegant. 2,000 to 6,000 seconds of specific impulse, 10 times better than any chemical rocket ever built. We had working prototypes. We had the nuclear devices. We had Freeman Dyson's calculations showing we could reach 11% of light speed. And then, in a supreme act of cosmic self-sabotage, we signed it all away. The Partial Nuclear Test Ban Treaty of 1963 didn't just end atmospheric nuclear testing. It murdered humanity's best chance to become an interplanetary species before the century's end. The story begins not with a eureka moment, but with a puzzle that haunted physicists through the dawn of the atomic age. In 1946, Stanislaw Ulam, the mathematical genius who would later help design the hydrogen bomb, scribbled an equation that would change everything. What if, instead of trying to contain nuclear explosions, we rode them? Think of it this way. Every chemical rocket is fundamentally a controlled explosion pointed downward. We burn fuel, create expanding gas, and Newton's third law does the rest. But chemical reactions release energy like striking a match, while nuclear reactions release energy like detonating a star. The energy density difference isn't just significant. It's the difference between crawling and teleporting. The breakthrough came during Operation Teapot in 1955. In the Nevada desert, where the sand had been turned to glass by previous atomic tests, scientists arranged basketball-sized spheres at various distances from ground zero, some naked steel, others coated in graphite. The prediction was total annihilation. The result defied every expectation. When the 14-kiloton blast wave hit, a wall of plasma hotter than the sun's surface moving at 100 kilometers per second, something miraculous happened. The graphite coating on certain spheres didn't just melt or burn, it sublimated instantly, jumping straight from solid to gas in microseconds. This created what physicists call an ablative shield, a bubble of expanding gas that pushed the main blast wave away from the sphere's surface. Like a silk scarf protecting your hand as you pass it quickly through a candle flame, the vaporizing graphite saved the steel beneath. But here's where it gets cosmic. These spheres didn't just survive, they flew. The asymmetric ablation on one side created thrust. Nature had just demonstrated the principle of nuclear pulse propulsion, and Lou Allen was there to witness it. By winter 1957, Ted Taylor at Los Alamos, a man who could design nuclear weapons the way Mozart composed symphonies, joined forces with Freeman Dyson at General Atomics. Dyson, taking sabbatical from Princeton, brought the mathematical rigor of theoretical physics. Taylor brought the practical knowledge of nuclear explosives. Together, they calculated something extraordinary. A properly designed plate could capture 85% of a nuclear blast's momentum while surviving thousands of detonations. The physics were undeniable. If you detonated a 1-kiloton device 60 feet behind a massive steel plate coated with oil, the oil would vaporize into a plasma jet. This jet, expanding at tens of kilometers per second, would strike the plate like a giant's palm, delivering a crisp 30 meters per second of velocity change. String these explosions together. Boom, boom, boom. And you're not just reaching orbit. You're reaching relativistic velocities. To understand the audacity of Project Orion's engineering, imagine you're tasked with building a ship that must survive being repeatedly kicked by nuclear bombs, smooth those kicks into comfortable acceleration, and do it all while carrying enough atomic fuel to tour the solar system. Oh, and the crew needs to survive. The spacecraft they designed was a monument to controlled insanity. Picture the Empire State Building laid on its side, made of steel, and fitted with the universe's most violent engine. At 80 meters tall and 40 meters wide, Orion would have dwarfed every spacecraft we've built since. The International Space Station could fit inside its cargo bay. At Orion's heart lay 4 engineering miracles, each solving an impossible problem. The pusher plate. Imagine a steel disc the size of a baseball diamond, 4 meters thick at the center, tapering to knife edges. This wasn't just armor. It was a momentum transfer device that would face nuclear hellfire every 3 seconds and ask for more. The secret was its coating. A thin layer of oil or plastic that would vaporize with each blast, carrying away heat while the steel beneath remained cool. Like a boxer's glove distributing the punch, the plate would spread each nuclear hammer blow across its entire surface. Nuclear pulse units. These weren't crude atom bombs, but precision-engineered propulsion charges. Each unit, about the size of a hat box, contained a tiny nuclear device wrapped in a tungsten casing. When detonated, the tungsten would vaporize into a directed plasma jet, focused like a shaped charge toward the pusher plate. During launch, these 0.1 kiloton units would detonate every second. Once in space, larger 20 kiloton units would fire every few seconds. The ship would carry 800 of them in revolving magazines, like bullets in the Devil's Own machine gun. The shock absorption system. This was the magic that transformed nuclear violence into smooth acceleration. Picture a 2-stage system. First, massive toroidal gas bags, like enormous steel donuts filled with helium directly behind the pusher plate. These would compress with each blast, absorbing the initial spike. Behind them, 4 telescoping pistons, each the size of a subway car, connected the pusher to the main spacecraft. Together, they transformed the sharp kick of each explosion into a steady 1.25 grams push, about what you'd feel in a sports car accelerating hard. Astronauts could walk around during thrust, sipping coffee while nuclear bombs exploded beneath their feet. The Pulse Delivery System. Essentially a nuclear bomb vending machine. Every 3 seconds, a mechanical arm would grab a pulse unit from the magazine, slide it down a launch tube, and fire it through a hole in the pusher plate. The bomb would travel 60 feet behind the ship, detonate, and the cycle would repeat. The precision required was extraordinary. Mistiming by even a fraction of a second could destroy the ship. In November 1959, they built a proof of concept called Hot Rod, a 1-meter model powered by conventional explosives. In a field in California, this tiny prototype rode 6 sequential blasts up to 100 meters, proving the impossible. You really could fly by setting off bombs under your spacecraft. The engineers celebrated with champagne while the model's parachute brought it safely back to Earth. Freeman Dyson ran the numbers obsessively. An atomic-powered Orion could achieve velocities of 3 to 5% of light speed. Replace the fission units with fusion bombs, and you could hit 10%. At those speeds, Alpha Centauri, our nearest star, transforms from an impossible dream to a 40-year journey. Within a single human lifetime, we could touch another sun. Every great tragedy needs its villains, but Orion's death came from something worse than malice. It died from fear, bureaucracy, and humanity's inability to see past its own shadow. NASA, created in 1958 as a civilian agency born from Cold War paranoia, wanted nothing to do with nuclear weapons. The agency's administrators, trying to sell space exploration to Congress and the American public, had chosen the moon as their target, and chemical rockets as their steeds. Apollo was safe, photogenic, and politically palatable. Orion was none of these things. As one NASA official reportedly said, "We're trying to send American heroes to the moon, not nuclear bombers to Mars." The Air Force saw different possibilities, darker ones. In 1959, when they took over Orion's funding, generals began sketching plans that would have made Dr. Strangelove proud. Orbital battle platforms carrying nuclear weapons, doomsday Orions, that could rain atomic death from space, deep space interceptors that could hunt enemy satellites throughout the solar system. One classified study proposed a 10,000-ton Super Orion that could carry 500 nuclear warheads to any point in the solar system. The scientists who dreamed of exploring Saturn's rings watched in horror as their Starship became a weapon. Meanwhile, the public was learning what atmospheric nuclear testing really meant. By 1963, strontium-90 from bomb tests was showing up in children's teeth. Every thunderstorm brought radioactive rain. The Limited Test Ban Treaty, signed on August 5, 1963 by Kennedy, Khrushchev, and Macmillan, banned nuclear explosions in the atmosphere, underwater, and in outer space. It was a treaty born from humanity's first glimpse of planetary-scale self-destruction. For Orion, it was a death sentence written in diplomatic ink. The treaty went into effect October 10, 1963. And suddenly, the most promising propulsion system ever developed became illegal under international law. NASA quietly withdrew its support. The Air Force, denied their orbital weapons platform, lost interest. By 1964, Project Orion was officially canceled, having spent just $11 million over 7 years, less than the cost of a single Saturn V launch. Freeman Dyson would later write with barely controlled fury, "This is the first time in modern history that a major expansion of human technology has been suppressed for political reasons." He calculated that if Orion had been developed instead of Apollo, we could have established a 100-person Mars base by 1985 for the same cost as landing 2 men on the moon. Ted Taylor, watching his life's work cremated by bureaucracy, made one last attempt. He proposed launching Orion from the moon or from deep space, avoiding the treaty restrictions. Nobody listened. The man who had shown humanity how to ride nuclear explosions to the stars spent his last years advocating for nuclear disarmament. His dreams of interplanetary civilization buried beneath the weight of what might have been. But physics doesn't forget. The equations that made Orion possible still whisper from textbooks, waiting for humanity to remember its courage. In June 2000, at a small aerospace company called Andrews Space, a team of engineers decided to resurrect the dream, but with a 21st century twist that would sidestep every political landmine that killed the original. Mini-Mag Orion is nuclear pulse propulsion reborn for the age of magnetic confinement. Instead of nuclear bombs, picture fuel pellets smaller than aspirin tablets, each containing less than 100 grams of fissile material. Instead of chemical explosives, imagine magnetic fields powerful enough to crush atoms. It's the difference between using dynamite and using a precision laser. Same physical principle, radically different execution. Here's how it works. A pellet of uranium-235 or plutonium wrapped in a shell of conducting material gets injected into a magnetic compression chamber.
2.
Capacitor banks carrying the energy of a lightning bolt dump their charge in microseconds, creating a magnetic field so intense it could levitate a freight train. This field crushes the pellet in what physicists call a Z-pinch. Imagine an invisible fist squeezing the pellet from all directions simultaneously.
Scooter, no action.
The compression triggers fission, but in a controlled, confined manner. No mushroom cloud, no fallout, just pure directed thrust. The innovation is breathtaking in its elegance. Magnetic nozzles, essentially electromagnetic fields shaped like invisible rocket bells, capture and direct the expanding plasma.
Atlantis on its way. All
Even
3
better,
engines now
they can
throttling
recapture
down
part
as
of the
area
energy
begins
from
as
each
the
pulse
vehicle
to charge
passes
the
through area of
capacitors for
maximum
the next
dynamic
one.
pressure.
It's nuclear
Atlantis,
propulsion that powers
Houston,
itself,
no action
each
on the
explosion
NTSB
making the next one
QRP.
easier. Andrews Space, working with Sandia National Laboratories' Z-machine, a magnetic pulse generator the size of a warehouse, demonstrated that the physics worked. They showed that mylar films could direct current into fuel pellets, creating the imploding magnetic fields needed for compression. The results were everything they hoped. Specific impulse exceeding 10,000 seconds, thrust comparable to the Space Shuttle main engine, and efficiency that makes chemical rockets look like burning coal in the age of fusion. The performance numbers read like science fiction. 100 tons to Mars in 3 months. Jupiter in 1 year. A crewed mission to Neptune, in less than 5 years. With Mini-Mag Orion, the entire solar system becomes as accessible as low Earth orbit is today. Yet here we are in 2025, and Mini-Mag Orion remains a paper spacecraft, unfunded and unbuilt. The tragedy isn't technical. Every component has been demonstrated. It isn't even political. No treaties ban magnetic confinement fusion in space. The tragedy is one of imagination. We've become so accustomed to the slow boats of chemical propulsion that we've forgotten to demand the starships physics says we could build. Step outside tonight and look at Mars. That red point of light that has captivated humanity since we first looked up. With our best current technology, astronauts heading there will watch Earth shrink to a point of light over 9 months of travel, aging a year for a round trip, facing radiation, muscle atrophy, and the psychological toll of extreme isolation. Now imagine a different timeline, one where courage trumped fear in 1965, where Freeman Dyson's Orion rose on nuclear fire from the Nevada desert, carrying not weapons but scientists, not warheads but greenhouses. By 1970, nuclear pulse ships would be ferrying colonists to Mars in 10-week luxury cruises. By 1980, we'd have research stations on Jupiter's moons. By 1990, human beings would be standing beneath the rings of Saturn, looking back at Earth as a pale blue dot not through robotic eyes, but through the visors of their helmets. We had this future in our hands. The blueprints still exist, archived in filing cabinets at NASA and Los Alamos. Dyson's calculations, showing we could reach 11% of light speed with fusion pulse propulsion, remain as valid today as when he scribbled them in 1958. The hot rod test footage, showing that tiny model riding explosion after explosion into the California sky, proves it wasn't fantasy. We chose to abandon this technology not because it didn't work, but because we were afraid of what it meant. Afraid of the nuclear genie. Afraid of militarization. Afraid of taking the giant leap that physics offered us. Every Mars mission delayed. Every probe that takes decades to reach the outer planets. Every astronaut who spends a year of their life traveling to our nearest planetary neighbor. They're all monuments to our self-imposed limitations. We're like sailors who discovered steam engines but chose to keep using wind, afraid the boilers might explode. The question for our generation isn't whether nuclear pulse propulsion works. We proved it does with slide rules and vacuum tubes. The question is whether we'll ever again possess the combination of vision, courage, and desperation that made the Apollo program possible. Because out there, beyond Earth's magnetosphere where treaties don't apply and fallout doesn't matter, the physics that could carry us to the stars in years instead of centuries is still waiting. Minimag Orion could be built with today's technology for less than the cost of a single Mars mission using chemical rockets. But it sits unfunded while we continue to accept the tyranny of the rocket equation, prisoners of our own timidity. Perhaps what we need isn't better technology, but better dreams. Dreams big enough to make us reconsider the calculated risks of nuclear propulsion against the certain stagnation of remaining Earthbound. Dreams that remind us that every moment we delay, the stars grow older, and so do we. Tell us, would you board a nuclear pulse spacecraft knowing the risks if it meant seeing Saturn's rings with your own eyes? Or have we made the right choice, keeping this atomic genie locked away while we inch across the cosmos on chemical flames? Is safety worth the stars? Because somewhere in an alternate universe, there's a version of humanity that said yes to Orion. And tonight, while we look up at Mars through telescopes, they're looking down at it through windows. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
In 1991, deep inside a classified facility, a team of American engineers watched their creation come to life for the first time. The particle bed reactor held together. The system worked. For a brief, electrifying moment, they had done it. They'd built a rocket engine that could revolutionize spaceflight, reaching Mars in a fraction of the time of any chemical rocket. But, as one technician would later recall, seeing the system hold together was like watching a miracle unfold. What they didn't say out loud was what they were all thinking. They'd also created something that could spread radioactive contamination across entire continents if it failed. This is the story of Project Timberwind, the most powerful rocket engine ever built, and the dark secret of why it was buried before it ever flew. To understand why Timberwind mattered, you first need to understand the prison that has confined spaceflight since the very beginning. It's called the rocket equation, and it's as beautiful as it is cruel. The mathematics are elegant, simple even, but their implications are devastating. Every kilogram of payload you want to carry requires fuel, but that fuel has mass, which means you need more fuel to carry the fuel. And that additional fuel has mass, requiring even more fuel. It's an exponential spiral, a tyranny of diminishing returns, that has haunted every rocket engineer who ever lived. Chemical rockets, the kind we've relied on since the dawn of the space age, face a hard physical limit. They work by burning fuel and oxidizer, creating hot gases that rush out the back, pushing the rocket forward. The hotter those gases, the faster they move, and the more efficient your rocket becomes. We measure this efficiency with something called specific impulse. Essentially, how many seconds a rocket can produce thrust from a given amount of propellant. It's the miles per gallon of spaceflight. And here's the problem. Chemical rockets, no matter how cleverly designed, max out around 450 seconds of specific impulse. That's it. That's the ceiling. The chemistry simply won't allow anything higher. This limitation isn't just academic. It defines what's possible in space exploration. With chemical propulsion, a mission to Mars takes 8 to 9 months of transit time. That means 8 to 9 months of life support, radiation exposure, bone loss, and psychological strain for any crew. It means massive spacecraft to carry all the supplies needed for that journey. It means launch windows that only open every 2 years when Earth and Mars align favorably. The rocket equation doesn't just make Mars missions difficult, it makes them almost prohibitively expensive and dangerous. But what if you could shatter that ceiling? What if, instead of chemical combustion, you used a nuclear reactor to heat your propellant? Nuclear reactions release millions of times more energy than chemical reactions. In theory, you could heat hydrogen propellant to temperatures that chemical combustion could never achieve, producing exhaust velocities that would make chemical rockets look like horse-drawn carriages next to a supersonic jet. This was the promise of nuclear thermal propulsion, and it had captivated a small community of physicists and engineers for decades. Among them was Dr. George Miley, a pioneering nuclear physicist whose fascination with atomic power had driven him to believe that nuclear propulsion was humanity's only realistic path to the stars. For Miley, this wasn't just about engineering specifications, it was about vindication. He'd spent decades championing nuclear technology for peaceful purposes, watching public fear and political resistance repeatedly thwart promising applications. Nuclear thermal propulsion represented a chance to prove that atomic energy could be more than weapons and accidents, that it could be the key that unlocked the solar system. The concept was straightforward enough. Build a nuclear reactor, pump hydrogen propellant through it, let the reactor heat the hydrogen to extreme temperatures, and exhaust it through a nozzle. Early nuclear thermal concepts promised specific impulses of 800 to 900 seconds, nearly double what chemical rockets could achieve. Run the numbers, and suddenly Mars missions could be measured in weeks rather than months, 6 to 8 weeks potentially, instead of 8 to 9 months. The implications were staggering. Shorter missions meant less radiation exposure, less life support mass, smaller spacecraft, lower costs, and dramatically reduced crew health risks. This wasn't idle speculation. NASA had actually built and tested nuclear rocket engines in the 1960s and early 1970s under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. They worked, they produced the promised performance, but they had one fatal flaw. They were heavy, incredibly, prohibitively heavy. The problem was fundamental to the design. NERVA-style engines use solid fuel elements, essentially rods of uranium arranged in a reactor core. The hydrogen propellant flowed through channels in these fuel rods, absorbing heat. But solid fuel rods required massive structural support to prevent them from vibrating apart in the intense flow. They needed heavy radiation shielding to protect nearby components. They needed thick pressure vessels and elaborate cooling systems. When you added it all up, yes, You got better specific impulse than chemical rockets, but the engine itself weighed so much that the overall performance advantage largely evaporated. If your nuclear engine weighs 3 times more than a chemical engine, but only provides twice the efficiency, you haven't actually gained much. This was the wall that nuclear propulsion had hit. The challenge wasn't just making a nuclear rocket, it was making one light enough to actually provide a meaningful advantage. For years, it seemed like an intractable problem. The very nature of nuclear reactors, the shielding, the structure, the safety systems, seemed to demand mass that negated the performance benefits. And that's where Dr. Leonard Wood entered the story, with an idea so radical, so counterintuitive, that it would either revolutionize spaceflight or fail spectacularly. Wood was a rocket engineer with a reputation for relentless optimism and engineering brilliance. Where others saw intractable problems, Wood saw opportunities for radical rethinking. He looked at the Nerva design and asked a simple question: what if we got rid of the solid fuel rods entirely? His alternative was audacious. Instead of solid fuel elements requiring heavy structural support, what if you use thousands of tiny fuel particles, each smaller than a grain of sand, suspended in the flowing hydrogen propellant itself? The propellant flow would keep the particles suspended and separated, eliminating the need for structural supports. The particles would have enormous surface area relative to their volume, allowing for much more efficient heat transfer. And because the particles were small and could withstand higher temperatures without melting, you could run the reactor much hotter than solid fuel elements would allow. Wood described it as a fluidized bed coffee percolator. Imagine coffee grounds suspended and agitated by boiling water, dancing in the turbulent flow. Now, imagine those coffee grounds are actually tiny spheres of uranium fuel, and the water is hydrogen moving at supersonic speeds, being heated to temperatures that would vaporize steel in seconds. That was the particle bed reactor concept. The advantages were compelling. The dramatically increased surface area meant better heat transfer. You could extract more energy from the nuclear reaction and dump it into the propellant more efficiently. The elimination of heavy structural supports meant a much lighter engine, and the ability to operate at higher temperatures meant higher performance. Timberwind's particle bed reactor was designed to achieve a specific impulse of 900 to 1,000 seconds, more than twice the efficiency of contemporary chemical rockets. But the real breakthrough was in the thrust-to-weight ratio, how much thrust an engine produces relative to its own weight. This is critical, because a heavy engine eats into your payload capacity. Nerva-style engines achieved thrust-to-weight ratios of 3.1 or 4.1, decent, but not spectacular. Wood believed Timberwind could achieve ratios of 15.1 or higher. That would approach the performance of chemical rockets while maintaining the efficiency advantages of nuclear propulsion. It was, potentially, the best of both worlds. The concept was brilliant on paper, but it introduced a terrifying new variable. Those thousands of tiny fuel particles had to remain perfectly suspended in supersonic flow. The physics was delicate, dependent on precise flow velocities and turbulence patterns. If the flow became unstable, if particles began to clump together or settle in one region of the reactor, you could get localized hotspots. Fuel particles could melt. They could agglomerate into larger masses. They could escape the reactor entirely, and every one of those particles was radioactive. A catastrophic failure of flow stability didn't just mean engine failure, it meant potential release of radioactive material. But Wood was convinced the physics would work. The question was whether he could convince anyone else, particularly the people who controlled the funding, and as it happened, the timing couldn't have been more perfect. In the mid-1980s, the Strategic Defense Initiative, popularly known as Star Wars, was consuming billions of dollars in pursuit of an ambitious goal: developing space-based weapons systems capable of intercepting Soviet nuclear missiles. The concept required spacecraft that could maneuver rapidly in orbit, changing trajectories quickly to intercept incoming warheads. Chemical rockets couldn't provide the necessary performance. They couldn't deliver the delta V, the change in velocity needed for the kind of aggressive orbital maneuvering the mission required. Nuclear thermal propulsion was identified as a key enabling technology, and Wood's particle bed reactor concept, with its promise of high thrust-to-weight ratios and excellent specific impulse, looked like exactly what SDI needed. Around 1987, Project Timberwind was born as a black budget program under the Strategic Defense Initiative Office, with funding and oversight from the Air Force and Department of Energy. It was classified from the beginning. Compartmentalized research, need-to-know restrictions, facilities within facilities. The team drew researchers from national laboratories including Los Alamos and Brookhaven, aerospace contractors, and military liaisons. They worked under extreme pressure and intense secrecy, surrounded by security protocols and the constant presence of armed guards. For Miley, Wood, and the rest of the team, the secrecy was both thrilling and isolating. For the first time, we felt we could actually build a rocket engine that would change the future of spaceflight, Dr. George Miley would later recall. The sense of urgency and secrecy only heightened our commitment. They were working on technology that could genuinely transform humanity's relationship with space, but they couldn't tell anyone about it. There was a profound irony in the arrangement. A project designed to enable weapon systems was also humanity's best shot at efficient deep space propulsion. The same engine that could power a missile interceptor could also power a Mars mission. Military funding was making possible what civilian space agencies had been unable or unwilling to pursue. But that military connection would later become a liability. Secrecy came with a price. The very classification that protected Timberwind also isolated it from the broader scientific community. Peer review was limited to those with the appropriate clearances. Independent safety analysis was restricted. And most critically, the public, whose support would ultimately be necessary for any nuclear rocket program, had no idea this technology even existed. The team was building something revolutionary in a bubble, cut off from the normal mechanisms of scientific discourse and public accountability. While the world remained oblivious inside those classified facilities, the team was about to face their first major test, proving that particles could actually stay suspended at the temperatures and flow rates required. The engineering challenges were formidable. First, there was the materials problem. You needed fuel particles that could withstand temperatures exceeding 3,000 Kelvin, hot enough to melt most metals, while maintaining structural integrity and not reacting chemically with hydrogen. The particles needed specialized coatings, carefully engineered compositions, and manufacturing precision measured in microns. Then there was the flow dynamics problem. Achieving the precise velocity and turbulence needed to keep particles suspended without creating destructive vibrations or pressure oscillations required sophisticated understanding of fluid mechanics at extreme conditions. The mathematics were complex, the experimental validation even more so. Early tests revealed problems no one had anticipated. Flow instabilities caused particles to migrate to certain regions of the reactor. Unexpected erosion patterns appeared. Pressure oscillations threatened to tear components apart. And always, lurking behind every test, was the threat of fuel particle escape, radioactive material breaching containment. The team adopted an incremental approach, building confidence through hundreds of smaller tests. They started with non-nuclear simulant particles, gradually increasing temperatures and flow rates. They developed novel injector designs to create the right flow patterns. They built real-time monitoring systems using advanced sensors that could track particle behavior inside the reactor during operation. They designed test stands with remote operation capabilities and extensive radiation monitoring, with emergency shutdown systems that could kill the reactor in milliseconds if parameters went out of bounds. The psychological toll was significant. These were engineers and scientists working with systems that could fail catastrophically. Every test carried the awareness of radiation exposure risks, the pressure of the classified environment, the inability to discuss their work with colleagues outside the program, the constant security scrutiny added another layer of stress. And then came 1991. In a series of critical tests, the particle bed reactor prototype held together under conditions approaching operational parameters. The fuel particles remained suspended. The flow stayed stable. The heat transfer performed as predicted. The system worked. Seeing the system hold together was like watching a miracle unfold, one technician observed. It was a moment of triumph, proof that Wood's radical concept wasn't just theoretical speculation, but actual functioning hardware. They had done something no one else had achieved. They had built a particle bed reactor that operated at nuclear thermal propulsion conditions. But that relief was tinged with something else, a growing realization of what they'd actually created. Because proving the concept worked in a test stand was one thing. Actually flying, it was something else entirely. They had to confront an uncomfortable question. What happens when you try to launch this thing? Any nuclear rocket must be launched on a chemical rocket first. There's no other way to get it off the ground. That means a fully fueled nuclear reactor containing substantial amounts of enriched uranium, sitting atop tons of explosive chemical propellant during the most dangerous phase of flight. Launch is when most rocket failures occur. The stresses are enormous. The systems are pushed to their limits. And the consequences of failure are immediate and catastrophic. The team began systematically analyzing the failure scenarios. A launch pad explosion would scatter radioactive fuel across the launch site and downwind areas. An in-flight breakup would distribute contamination along the trajectory. A failed orbital insertion could cause uncontrolled re-entry, with the reactor burning up in the atmosphere and spreading material across a wide area. Even with fuel particles designed to survive re-entry intact, encased in protective coatings meant to withstand the heat, a catastrophic failure could spread detectable radioactive material across thousands of square miles. The contamination might not be lethal in most areas, but it would be measurable, persistent, and politically explosive. Then there was the activation problem. Once a nuclear reactor operates, even briefly, neutron radiation activates the materials in the reactor structure itself. The engine becomes intensely radioactive, not just the fuel, but the metal components, the plumbing, everything. That radioactivity persists for decades. A spent Timberwind engine would be a permanent piece of radioactive space debris, too hot to safely approach or dispose of. And even during normal operations, the engine would vent small amounts of radioactive hydrogen. The quantities might be tiny, the radiation doses negligible compared to natural background. But the optics were terrible. You'd be deliberately releasing radioactive material into the environment as part of routine operations. There was precedent for concern. The Soviet Union had flown nuclear-powered satellites, and in 1978, one of them, Cosmos 954, had malfunctioned and re-entered over northern Canada, scattering radioactive debris across a wide area. The cleanup operation was expensive and politically damaging. The incident had heightened international sensitivity about nuclear materials in space. The regulatory landscape was equally daunting. No framework existed for licensing nuclear rocket launches. Public acceptance was uncertain at best. International treaties restricted certain uses of nuclear materials in space. The team was navigating uncharted territory, both technically and politically. They began running probabilistic risk assessments, statistical models of every possible failure mode, weighted by likelihood and consequence. The numbers were sobering. Even with multiple redundant safety systems, even with the most conservative operational procedures, the probability of some radioactive release during a launch campaign involving multiple flights was not negligible. The question became impossible to avoid. How much risk is acceptable? How many potential deaths per mission can you justify? 1, 10, 0? And who gets to make that decision? The engineers who built the system, the military officers who wanted to use it, the politicians who funded it, or the public who would bear the consequences. Dr. Miley, the nuclear physicist who had championed this technology for decades, found himself confronting doubts he'd never expected. He understood radiation risks intellectually. It was his field of expertise. But there's a difference between academic understanding and practical responsibility. The dream of nuclear spaceflight, which had driven his career, was now forcing him to grapple with questions that had no easy answers. And then, just as these questions were becoming impossible to ignore, the world shifted beneath them, literally overnight. November 1989. The Berlin Wall fell. December 1991. The Soviet Union formally dissolved. The Cold War enemy that had justified the Strategic Defense Initiative simply ceased to exist. The geopolitical context that had birthed Timberwind evaporated. The impact was immediate. SDI funding was slashed. Priorities shifted from space-based weapons to more terrestrial concerns. Nuclear programs, already politically sensitive, became toxic. The peace dividend meant cutting defense spending, and expensive exotic programs like Timberwind were easy targets. For Dr. Wood, it was crushing. His life's work, the revolutionary engine that could change spaceflight forever, was suddenly irrelevant. He tried to pivot, to find new justifications in a world that no longer feared Soviet missiles. Mars missions, he argued. Deep space exploration. Scientific advancement. But without the military urgency, without the existential threat of the Cold War, the political will evaporated. The budget reality was stark. Timberwind would require hundreds of millions more dollars to reach flight-ready status. In the new political environment, that funding wasn't coming. The project limped along for a while, sustained by bureaucratic momentum and the hopes of true believers. But the trajectory was clear. By the mid-1990s, Project Timberwind was effectively dead, buried under classification and bureaucratic indifference. The particle bed reactor that had held together in those triumphant 1991 tests would never fly. The revolutionary propulsion system that could have cut Mars transit times from months to weeks would never leave the test stand. The technology that represented decades of work and billions of dollars in investment was locked away, classified, largely forgotten. Today, the basic physics that made Timberwind promising hasn't changed. The rocket equation still imposes its tyranny on chemical propulsion. Mars is still 8 to 9 months away. Nuclear thermal propulsion would still offer dramatic advantages for deep space missions. But the political, environmental, and safety concerns that helped kill Timberwind remain unresolved. We're left with a profound question. Was Timberwind a tragedy of lost potential, or a cautionary tale of technology that was too dangerous to use? Were the engineers who built it visionaries whose work was cut short by political expedience, or were they brilliant people who created something that should never have been flown? Perhaps the answer is both. The technical achievement was real. They did solve problems that had stymied nuclear propulsion for decades. The particle bed reactor concept was genuinely innovative, but the safety concerns were also real. The risks weren't hypothetical. They were inherent in the technology itself. Project Timberwind remains classified to this day. Its full technical details still locked behind security restrictions. The engineers and scientists who worked on it are aging, taking their knowledge and experiences with them. The test hardware has been dismantled or sits in storage, radioactive and untouchable. But the dream hasn't died entirely. Interest in nuclear thermal propulsion persists. NASA and private companies continue to study the concept. New designs, new safety systems, and new political contexts may eventually make nuclear rockets viable. Perhaps future engineers will rediscover Timberwind's innovations, learning from both its successes and its failures. For now, though, Timberwind stands as a monument to a particular moment in history, when brilliant scientists built something extraordinary and terrifying, when the pursuit of unprecedented power forced a reckoning with consequence, and when humanity chose, perhaps wisely, to leave that power unused. The particle bed reactor held together. The system worked. But sometimes, the most important question isn't whether we can build something, but whether we should. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. On July 3, 1969, just 13 days before Apollo 11 would land on the Moon, one of the largest non-nuclear explosions in human history erupted on a launch pad in Kazakhstan. A Soviet rocket called the N-1, taller than a football field and powered by 30 engines, exploded 5 seconds after liftoff in a massive blast. The fireball mushroomed into the night sky, visible for 40 kilometers. A 40-ton crane was hurled over 1,000 meters like a child's toy. The launch pad, years of infrastructure and millions of rubles, simply ceased to exist. The Soviet state denied it ever happened. While America openly broadcast its moon ambitions with the Saturn V, the Soviet Union was building something even more audacious in complete secrecy. The N-1 rocket was the USSR's answer to Apollo, and it would become the most spectacular failure the world wasn't allowed to know about. This is the story of brilliant engineers forced to skip critical testing, a decades-long cover-up, and the true cost of the space race when national pride eclipses safety. Because when you cluster 30 rocket engines together without ever testing them as a complete system, you're not building a moon rocket. You're building the world's most expensive bomb. Standing 105 meters tall with a base diameter of 17 meters, the N-1 was a monster. Picture this. If you stood at its base and looked up, the rocket would tower over you like a 35-story building. Its total liftoff mass reached 2,735 metric tons, roughly the weight of 550 adult elephants, all balanced on a platform the size of a tennis court. This wasn't just a rocket, it was Sergei Korolev's ultimate vision, the man who had given the Soviets their greatest Cold War victories with Sputnik and Gagarin. For Korolev, the N-1 would cement Soviet technological superiority once and for all. But after Kennedy's 1961 moon challenge, Khrushchev demanded the Soviet Union reach the moon first, and provided no additional funding. Korolev had to build a Saturn V competitor on a shoestring budget, a mandate that would haunt every decision that followed. But here's where ambition collided with brutal physics. While the Saturn V's first stage relied on just 5 massive F1 engines working in harmony, the N-1's first stage featured 30 NK-15 engines, the most complex propulsion system ever attempted. Why 30? Because Soviet rocket engines were less powerful than American ones, and Korolev needed to compensate somehow. 30 engines meant 30 potential points of failure, creating unprecedented vibration and control challenges that Soviet engineers had never encountered before. Imagine trying to balance on a unicycle. Now imagine balancing on a unicycle while juggling. Now imagine doing that while 30 chainsaws are running inches from your body, and if even one chainsaw blade touches another, everything explodes. That was the N-1's first stage, a mechanical nightmare where the failure of a single component could cascade through the entire system in milliseconds. The program was so classified that even its failures remained state secrets. While NASA's setbacks played out on live television, the Soviet Union buried the N-1's disasters in silence. The goal was clear: achieve a crewed lunar landing and restore Soviet prestige after Apollo began surpassing their early space race victories. But that secrecy came with a brutal cost. No one outside the program could learn from their mistakes, and no one inside could admit the scale of the problems they faced. And those problems began with a feud between 2 brilliant men who refused to work together. The N-1's fate was sealed not by bad engineering, but by pride. Sergei Korolev and Valentin Glushko, 2 of the Soviet Union's most brilliant minds, despised each other so much that Glushko refused to build engines for Korolev's moon rocket. The bitter feud stretched back years, rooted in professional jealousy and clashing visions for Soviet spaceflight. Glushko, head of OKB-456 and the Soviet Union's premier rocket engine designer, had the expertise to create the powerful engines the N-1 desperately needed. But he wouldn't lift a finger to help Korolev's lunar dream. Instead, Korolev was forced to turn to Nikolai Kuznetsov's OKB-276, an aircraft engine bureau with zero experience building rocket engines. It was like asking a master watchmaker to build a suspension bridge. The result was the NK-15, each producing 1,500 kilonewtons of thrust. On paper, they looked adequate. In reality, they were oxygen-rich staged combustion engines, cutting-edge technology, but untested at this scale and prone to catastrophic failure if even one malfunctioned. And because no single engine could provide enough power, Korolev's team had to cluster 30 of them in the first stage alone, arranged in a circular pattern like a mechanical flower of death. 30 engines meant 30 potential failure points, all firing in unison just meters apart. The vibration was nightmarish. Acoustic feedback rattled through the structure like a tuning fork from hell. The control system struggled to compensate for the chaos. Engineers warned about these problems. They pleaded for time to test, to iterate, to understand what they were building. But political pressure to beat Apollo drowned out their concerns. Testing was deemed too expensive, too time-consuming. The Americans were racing ahead, and the Soviet Union couldn't afford to look weak. Then came the decision that would doom the entire program. No full-scale static test of the assembled first stage would ever be conducted. Building a test stand capable of containing 4,500 metric tons of thrust, enough force to lift the Eiffel Tower, would cost as much as the rocket itself and take years to build. Years they didn't have. So they decided to test the most complex rocket engine cluster in history by launching it and hoping it worked. It was engineering Russian roulette with a fully loaded chamber. Then, in January 1966, Korolev died unexpectedly during what should have been routine surgery. He was only 59. His successor, Vasily Mishin, inherited a rocket built on compromise and personal vendetta, a machine that had never undergone proper testing, facing an American Apollo program that was accelerating toward the moon with every passing month. Mishin was a brilliant mathematician, but lacked Korolev's political clout and charisma. He would need both. Because now, with untested engines, political pressure mounting, and the Americans racing ahead, Soviet engineers faced an impossible choice: test properly and lose the race, or launch and pray. They chose to launch. Between February 1969 and July 1969, the N-1 went from hope to horror in 2 launches that would define the program's legacy. The first attempt, N-1-3L, lifted off on February 21, 1969. For 68 seconds, it seemed like the impossible might work. The rocket climbed skyward, 30 engines roaring in unison, a pillar of fire ascending into the Kazakhstan sky. Engineers in the bunker held their breath. Then, at T plus 68 seconds, a loose bolt, a single piece of metal no bigger than your thumb, was sucked into a fuel pump. The engine exploded. The Cord automatic control system, designed to shut down failed engines and compensate with the remaining ones, tried to respond. But it couldn't handle the cascading failures. One engine failure triggered another, then another, like dominoes falling in a circle. The vibrations amplified. The rocket began to tumble. At 52 kilometers downrange, the N-1 crashed and exploded in a massive fireball visible from the cosmodrome. The world never knew. Soviet secrecy was absolute. But nothing compared to what happened 4 months later, July 3, 1969. Just 17 days before Neil Armstrong would step onto the moon, N-15L sat on its launch pad, fully fueled with 2,400 tons of liquid oxygen and kerosene. The countdown reached 0. Ignition. For half a second, 30 engines roared to life. Then engine number 8 ingested debris from the fuel line. It exploded instantly. The Cord system, faced with catastrophic failure at T plus 0.5 seconds, made a fatal decision. It shut down all engines simultaneously. The fully fueled rocket, taller than a 35-story building and weighing as much as a naval destroyer, hung in the air for a moment. Then it fell back onto the launch pad. What happened next was one of the largest non-nuclear explosions in human history. 2,400 tons of propellant detonated with the force of 7 kilotons of TNT, roughly half the yield of the atomic bomb dropped on Hiroshima. The blast wave flattened everything within a kilometer. The launch complex, years of construction, millions of rubles, the culmination of thousands of engineers' work, simply ceased to exist. A crater 60 meters wide opened in the earth. That 40-ton crane was found over a kilometer away, twisted like paper. Boris Chertok, a senior engineer, watched from a nearby bunker as the fireball consumed everything. The shockwave hit the bunker like a physical blow. The walls shook. Dust rained from the ceiling. Through the reinforced observation window, he saw the mushroom cloud rising into the night sky, illuminated from within by the burning propellant. He later described it as a blow not only to the rocket, but to the spirit of the team. Engineers who had spent years building the N1 watched their life's work vanish in seconds. Some wept. Others sat in stunned silence. Vasily Mishin, already suffering from chronic insomnia after the first failure, reportedly didn't sleep for 3 days. Incredibly, no one was killed. Most personnel had evacuated to bunkers before launch, but the psychological damage was immeasurable. Apollo 11 landed on the moon just 17 days after this catastrophe. But the Soviet Union couldn't admit defeat. Not yet. Mishin and his team would try 2 more times, each failure more desperate than the last. The third attempt came on June 27, 1971, N1-6. Represented 2 years of desperate modifications and improvements. Engineers had worked around the clock, improvising solutions to problems that proper testing would have revealed years earlier. They knew the program was likely doomed, but they couldn't abandon their life's work. This time, the rocket actually flew. For 51 seconds, it climbed skyward, reaching 7 kilometers altitude. For 51 seconds, it seemed like redemption might be possible. Then the engine vibrations, those same harmonics that engineers had warned about, caused the vehicle to roll uncontrollably. The automatic destruct system activated, and the rocket exploded 7 kilometers above the steppe. It was a small victory wrapped in failure. The rocket had flown, proving the basic design could work. But it also revealed that engine clustering created vibration harmonics that the core system couldn't compensate for. The problem wasn't just individual engine reliability, it was the fundamental physics of putting 30 rocket engines in close proximity. Imagine 30 opera singers standing in a circle, each singing a different note. Individually, they're perfect. But together, they create acoustic interference patterns. Some notes amplify, others cancel out, and the overall sound becomes chaotic. That was the N1's engine cluster, except instead of sound waves, it was structural vibrations that could tear metal apart. November 23, 1972, N1-7L, the 4th and final attempt. By now, America had conducted 6 successful moon landings. The political will to continue was evaporating like water on the lunar surface. But the engineers pressed on. At T plus 107 seconds, the rocket reached 7 kilometers altitude. Then a fuel line ruptured due to vibration-induced metal fatigue. The metal had literally been shaken apart by the engine cluster's harmonics. The rocket exploded. Vasily Mishin watched another fireball bloom in the sky. He had spent years of his life on this program, sacrificing his health, his sleep, his sanity. And for what? 4 explosions, 0 successes. The Americans had already won. The tragic irony was that the final 2 launches showed the N1 design was improving. With continued development, with the testing time and resources that had been denied from the beginning, it might have eventually succeeded. The NK-15 engines, for all their problems, were actually brilliant pieces of engineering. The keyword system was learning from each failure. The structural improvements were working, but political patience had run out. The engineers' years of work would be destroyed, not by technical impossibility, but by the same political pressure that had rushed them to failure in the first place. By 1974, with Apollo's success and the N1's repeated failures, the decision was made to cancel the N1 and effectively erase it from history. The order came from Valentin Glushko, the same man whose feud with Korolev had started this disaster. Glushko was now in charge after Mishin's dismissal, and his first act was to kill his rival's dream. All hardware was ordered destroyed. Documentation was classified. The program was erased from official history. For nearly 2 decades, the N1 would exist only as a rumor, a ghost story whispered among Western intelligence analysts. Then, in the 1990s, as the Soviet Union collapsed and Glasnost opened the archives, the truth emerged, and with it, a surprising revelation about the rocket's legacy. After the program's cancellation in 1974, the Soviet state moved swiftly to erase all evidence. Remaining 105 rockets were meticulously scrapped, 105-meter giants cut apart and buried in the Kazakhstani steppe. Launch facilities at Baikonur were dismantled, the blast craters filled in. Documents were classified at the highest levels. Engineers were forbidden from discussing their work. For nearly 20 years, the USSR denied the N1 had ever existed, shifting focus instead to space stations and automated missions, while the West celebrated Apollo's triumph. The secrecy worked. It contributed to the perception of total American dominance in space, obscuring the genuine technical achievements buried in the N1's wreckage. But it also caused lasting damage to Soviet engineering. By classifying all N1 documentation, the Soviet Union prevented its own engineers from learning from these failures, hampering future programs. The lessons were buried with the hardware. But here's where the story takes an unexpected turn. Those supposedly unreliable Kuznetsov NK-15 engines, the ones that clustered and failed so spectacularly, were later resurrected. In the 1990s, American company Aerojet purchased NK-33 engines, upgraded NK-15S, that had been hidden away in a warehouse for decades. These engines proved remarkably advanced and were used in America's orbital ATK Antares launcher. However, design modifications were necessary to ensure safe integration within the Antares rocket. The engines weren't the problem. The integration was. The lack of testing was. The political pressure was. The core lesson of the N1 is brutally simple. Rocket engineering cannot be rushed. The Saturn V succeeded partly because it underwent extensive ground testing. Every stage was fired repeatedly while bolted to the ground, allowing engineers to measure every vibration, every pressure fluctuation, every potential failure mode before the first launch. The N1 never had that luxury. Soviet engineers tested individual NK-15 engines, but never the assembled cluster of 30. They were forced to conduct their full-scale tests during actual launches, a process that was both financially ruinous and psychologically devastating. And today, if you watch a SpaceX Starship launch, you're witnessing the N1's vindication. Super Heavy, Starship's first stage, uses 33 Raptor engines, more than the N1's 30, directly echoing that ambitious clustering approach. But this time, it works. Why? Modern computer control manages what 1960s Soviet technology couldn't, where the N1's keyword system was essentially flying blind, making crude adjustments based on limited sensor data. Starship's computers make thousands of adjustments per second, monitoring every engine parameter in real time. SpaceX has conducted extensive ground testing, static fires where all 33 engines burn while the rocket remains bolted down, exactly the testing the N1 never received. And SpaceX's iterative philosophy, fail fast, learn faster, represents everything the N1 program was never allowed to do. The unsung engineers and technicians who worked on the N1 finally received recognition in the Glasnost era of the late 1980s. Their innovations, particularly those NK-15 engines, proved their work wasn't in vain. But recognition came too late for many. Korolev died before seeing his creation fly. Mishin was dismissed in disgrace. Countless engineers spent their best years on a project they knew was doomed but couldn't abandon. The N1 story serves as a cautionary tale for any program where political deadlines override engineering realities, from space programs to nuclear power to AI development. The most dangerous force in engineering isn't technical complexity. It's the pressure to declare victory before the work is done. We began with an explosion that the Soviet Union tried to erase from history, a catastrophic failure that seemed to prove the impossibility of their lunar ambitions. The fireball on July 3, 1969, consumed more than a launch pad and a rocket. It consumed years of work, billions of rubles, and the dreams of thousands of engineers who believed they could reach the moon. But the true story reveals something more nuanced than simple failure. The N-1 didn't fail because clustering 30 engines was impossible. SpaceX proves that today with 33 engines on Starship. The N-1 failed because political pressure transformed a solvable engineering challenge into an impossible deadline. The brilliant engineers of OKB-1 weren't defeated by physics. They were defeated by the same political system that demanded they achieve the impossible without the time or resources to do it properly. Sergei Korolev's feud with Valentin Glushko denied the program the engines it needed. Khrushchev's demand for victory without funding denied it the resources. The decision to skip full-scale testing denied it the data. And the wall of secrecy denied future engineers the lessons that failure teaches. Today, we see echoes of their struggle in every ambitious project, where political will clashes with engineering reality. When deadlines are set by press conferences rather than physics. When budgets are determined by politics rather than requirements. When failure must be hidden rather than learned from. The N-1's legacy isn't just one of failure. It's a reminder that the most dangerous force in engineering isn't technical complexity, but the pressure to declare victory before the work is done. Those NK-15 engines, the ones that failed so spectacularly, eventually flew successfully on American rockets. The clustering approach, the one that seemed impossible, now powers the world's most advanced launch system. The engineers, the ones who were forced to fail, created innovations that outlived the Soviet Union itself. The N-1 never reached the moon, but its shadow stretches across every launch pad where engineers still fight the same battle, the struggle to build tomorrow's miracles with today's resources, under yesterday's deadlines. In the end, the real explosion wasn't the 7 kilotons of TNT on July 3, 1969. It was the detonation of a dream. A reminder that in the unforgiving vacuum of space, ambition without patience doesn't launch rockets. It destroys them. The N-1 rockets are gone, scrapped, and buried in the Kazakhstani steppe. But their story refuses to stay buried, because it's a story that every generation of engineers must learn again. The cosmos doesn't care about your deadlines. Physics doesn't negotiate with political pressure. And the only way to reach the stars is to respect the unglamorous, time-consuming work of testing, failing, learning, and trying again. Which engineering challenge from the space race seemed most impossible to overcome? The N-1's 30-engine cluster, the Apollo computer with less power than your phone, or the heat shield that had to survive re-entry temperatures hotter than the sun's surface? Let me know in the comments what you think was the most audacious gamble of the space age. And if you want to explore more hidden stories from the Cold War space race, hit that subscribe button, because the cosmos is full of secrets that deserve to be told.
In July 1969, Neil Armstrong and Buzz Aldrin carried something to the moon that had nothing to do with geology or exploration. Strapped to their bodies, embedded in the spacecraft walls, tucked into equipment bays, were dozens of passive radiation dosimeters. Small, simple devices that would record every particle strike, every cosmic ray impact, every dose of radiation encountered during their journey through cislunar space. NASA's public explanation was straightforward. Measure cosmic ray exposure to understand the health risks of spaceflight. The real story is more complex and far more strategic. These measurements filled a gap that no satellite could reach. no high-altitude balloon could approximate, and no ground-based test could replicate. They provided real-time verification of radiation models that the Department of Defense needed to harden electronics against nuclear war. The data Apollo collected contributed to understanding how radiation disrupts circuits in the exact environment where America's early warning satellites would need to survive a Soviet first strike. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster, like and turn on notification. We focus on what was built, why it mattered, and where it really led. Now, back to the story. To understand why Apollo's radiation data mattered so much, we need to go back to July 9, 1962, and an event that changed everything the military thought it knew about nuclear weapons in space. At 11:00 p.m. Hawaiian time, a Thor rocket lifted off from Johnston Atoll, carrying a 1.4 megaton thermonuclear warhead. The missile climbed to approximately 250 miles altitude, well above the atmosphere, and detonated directly over the Pacific Ocean. The explosion was designated Starfish Prime, the largest nuclear test ever conducted in space. And what happened next caught everyone by surprise. The electromagnetic pulse from the detonation traveled at the speed of light. Within microseconds, it reached Honolulu, 900 miles away. Streetlights failed across Oahu. Burglar alarms triggered simultaneously throughout the city. Telephone systems crashed. Radio stations went dark. The pulse had induced massive voltage spikes in every long conductor, every power line, every antenna, frying electronics that had no protection against such an assault. But the immediate EMP was just the beginning. The explosion pumped the magnetosphere with high-energy electrons, creating artificial radiation belts that persisted for years. At least 6 satellites failed in the months following Starfish Prime. Telstar, the first commercial communications satellite, began experiencing problems within days and failed completely by February 1963. The Soviet Cosmos 5 satellite died. The UK's first satellite, Ariel 1, had its solar panels destroyed by the radiation. The military had just learned a terrifying lesson. Nuclear weapons in space could disable entire satellite constellations without ever touching them. And America's strategic deterrent was rapidly becoming dependent on satellites that could not survive the environment that nuclear war would create. The problem was fundamental. To harden electronics against radiation, you need to understand exactly what kinds of radiation they will encounter, at what energies, and in what quantities. You need to know how particles interact with shielding materials. You need to understand secondary radiation created when primary particles strike spacecraft structures. You need real measurements from the actual environment, not extrapolations from theory. Starfish Prime had provided some data, but it was a single-point measurement of an artificial event, the natural radiation environment in cislunar space, where satellites orbit and where nuclear detonations would occur during war, remained largely theoretical. High-altitude balloons could reach 100,000 feet, maybe 120,000 on a good day. Sounding rockets could briefly touch the edge of space, but sustained measurements from deep space, beyond Earth's protective magnetosphere, simply did not exist. Until Apollo. The dosimeters carried on Apollo missions were not sophisticated instruments. Most were passive devices, thermoluminescent dosimeters, and nuclear emulsion packs that simply recorded cumulative exposure. But their value was in their location and duration. For the first time, humans were carrying calibrated radiation detectors through the Van Allen belts, across cislunar space to the lunar surface and back again. The entire transit profile that a military satellite or weapon system might experience. Apollo 11 carried personal dosimeters on each crew member, plus additional detectors mounted throughout the command module and lunar module. The measurements were not classified, they appeared in NASA's official mission reports, but their military implications were never emphasized. According to NASA technical documentation, The crew received average skin doses of approximately 0.18 rad during the 8-day mission, with individual readings varying by roughly 20% depending on position within the spacecraft. These numbers seem small, and they are, for human health. But the detailed spectrum of particle energies and types that produce those doses was valuable for engineering. Apollo 12 expanded the dosimeter package. Conrad, Gordon, and Bean carried improved instruments that could distinguish between different radiation types. They measured not just total dose, but the contribution from galactic cosmic rays, solar particles, and secondary radiation produced by particle interactions with the spacecraft hull. This data fed into radiation transport codes that modeled how particles penetrate shielding. By Apollo 14, the dosimeter program had become systematic. NASA published comprehensive, technical reports on radiation measurements, data that was publicly available and could be accessed by any organization, including the Department of Defense. Every Apollo mission contributed to a growing database of measurements that ground-based accelerators could never replicate. The energy spectrum of galactic cosmic rays extends to billions of electron volts. No laboratory beam could approximate the complexity of the real space environment. The military applications were significant and specific. Early warning satellites in geosynchronous orbit needed to survive long enough to detect Soviet missile launches and transmit that data to NORAD. During a nuclear exchange, these satellites would be bathed in radiation from both natural sources and weapon effects. Their electronics needed hardening based on accurate models of particle flux and energy distribution. The Defense Nuclear Agency, responsible for understanding nuclear weapon effects, could use publicly available Apollo data to validate computer codes that predicted radiation damage to semiconductor devices. Silicon-based electronics are particularly vulnerable to ionizing radiation. High-energy particles create electron hole pairs in the semiconductor material, disrupting transistor operation. Heavier particles can cause permanent damage by displacing atoms in the crystal lattice. The models that predicted these effects benefited from experimental validation from the actual space environment. Apollo contributed to that validation. The dosimeter data helped refine understanding of the heavy ion component of galactic cosmic rays in certain energy ranges. This had direct implications for memory circuits in satellite computers, which were vulnerable to single-event upsets when a heavy ion passed through a memory cell. Improved characterization of the radiation environment contributed to new hardening techniques, including redundant memory systems and error correction codes that became standard in military spacecraft. But there was another aspect to Apollo's radiation mission that received little public attention. The spacecraft themselves served as testbeds for shielding configurations. The command module used an aluminum pressure hull with varying thickness in different locations. The lunar module had thinner walls to save weight. By placing dosimeters at multiple locations throughout both vehicles, engineers could measure how different shielding thicknesses affected radiation penetration. This data could inform the design of reconnaissance satellites and early warning systems. How much shielding was enough? Where should it be placed? What materials worked best? Apollo provided empirical answers to questions that had previously been theoretical. The timing was significant. The late 1960s and early 1970s saw rapid expansion of military space systems. The Defense Support Program, America's first dedicated missile warning satellites, began deployment in 1970. These satellites carried infrared sensors that could detect the heat signature of ICBM launches. They orbited at 22,000 miles altitude, well beyond Earth's magnetosphere, in the same general radiation environment Apollo had characterized. The designers of DSP satellites had access to Apollo radiation data through NASA's public technical reports. They could reference measurements of particle fluxes, energy spectra, and shielding effectiveness from cislunar space. Whether and to what extent specific design decisions relied on Apollo data versus other sources like nuclear tests and accelerator experiments remains unclear from available records. The same data was available to inform the development of hardened communication satellites. During the 1970s, the Air Force deployed the Defense Satellite Communications System, a constellation of satellites designed to survive nuclear war and maintain command and control links. These satellites needed radiation hardening that would allow them to function for hours or days in a degraded environment filled with weapon effects and enhanced natural radiation. Apollo's contribution extended beyond simple dose measurements. The missions also carried nuclear emulsion detectors, thick photographic films that recorded the tracks of individual particles. When developed and analyzed under microscopes, these emulsions revealed the charge and energy of each particle that passed through them. This provided detailed information about the heavy ion component of cosmic rays, particles with high atomic numbers like iron or nickel nuclei traveling at relativistic speeds. These heavy ions were particularly concerning for electronics. A single ion nucleus passing through a transistor could deposit enough energy to flip bits in computer memory or trigger false signals in logic circuits. The phenomenon, called single event upset, was poorly understood in the 1960s. Apollo's emulsion data helped characterize the heavy ion flux in cislunar space, contributing to better understanding of single event effects and improved hardening techniques. The Apollo 16 mission in April 1972 carried the most comprehensive radiation package of any lunar flight. In addition to standard dosimeters, the crew deployed the cosmic ray detector on the lunar surface, an experiment that continued measuring particle fluxes for approximately 3 years after deployment. The data from this instrument, combined with measurements from the command module during transit, provided a detailed picture of the radiation environment from Earth orbit to the lunar surface. By the time Apollo 17 flew in December 1972, NASA had accumulated radiation measurements from 9 lunar missions covering different phases of the solar cycle. The Sun's activity varies on an 11-year cycle, and solar activity dramatically affects the space radiation environment. Solar flares can produce intense bursts of energetic particles. The solar wind modulates the flux of galactic cosmic rays. To design satellites that would operate for years or decades, engineers needed to understand radiation variations across the entire solar cycle. Apollo missions flew during solar cycle 20, which peaked in 1968 and reached minimum in 1976. The early Apollo flights occurred near solar maximum, when solar particle events were more frequent, but galactic cosmic ray flux was lower due to solar wind shielding. Later missions flew during the declining phase of the cycle, encountering higher cosmic ray fluxes. This natural variation provided data across different radiation environments, all of which was publicly available through NASA technical reports. The Department of Defense never publicly acknowledged specific use of Apollo's radiation data in satellite design. There was no particular reason to. The data appeared in NASA technical reports, available to anyone who wanted to read them. Military programs could simply reference the information alongside data from nuclear tests, accelerator, experiments, and dedicated military satellites. The implications were nonetheless significant. Radiation-hardened satellites launched during the Cold War could benefit from measurements that Apollo provided. The reconnaissance satellites that monitored Soviet missile silos, the communication satellites that would relay nuclear launch orders, the navigation satellites that guided weapons to their targets, all could incorporate hardening techniques informed by data from the same radiation environment that men experienced when they walked on the moon. There is something striking about this dimension of Apollo. The program is remembered for flags and footprints, for Kennedy's challenge and Armstrong's words, for the triumph of exploration and the inspiration of achievement. All of that is real and important, but the program also existed within broader strategic calculations about nuclear war and satellite survivability, about maintaining deterrence and preparing for conflict. The dosimeters the astronauts wore were measuring cosmic rays for NASA's stated purpose of understanding astronaut health, but that same data, published in technical reports, was available to inform the design of systems with military applications. The same measurements that helped protect astronauts from radiation also helped characterize the environment in which military satellites would need to operate. This is not a criticism. It is simply the reality of Cold War technology development. Every major program existed in a context where civilian and military applications overlapped. Every capability had potential dual uses. The lines between exploration and strategic advantage were always permeable. Apollo existed in that environment, genuinely advancing human knowledge while producing data relevant to multiple purposes. The astronauts themselves were largely test pilots and engineers, most with military backgrounds. They understood the broader context in which their missions operated, even if the specific applications of their dosimeter readings were not their primary concern. This was the Cold War. Technology served multiple purposes. After Apollo ended, the radiation data continued to provide value. The Space Shuttle program used Apollo measurements to design crew dosimeters and establish radiation exposure limits. The International Space Station planning process referenced Apollo data when determining shielding requirements for long-duration missions. Even today, NASA's Artemis program, planning to return humans to the Moon, uses Apollo radiation measurements as baseline data for crew safety analysis. The data also remained available to inform military satellite design. Through the 1970s and 1980s, as satellite technology advanced and new systems deployed, Apollo's radiation database represented one of several sources for cislunar environment characterization. Robotic satellites could carry dosimeters, and many did, but the systematic measurements from Apollo, with known detector positions and carefully calibrated instruments, remained a valuable reference. Technical reports from the 1970s that analyzed nuclear weapon effects on satellites, studied hardening techniques for electronics, and developed models for predicting system survivability drew on multiple data sources. Apollo measurements were part of this body of knowledge, alongside data from nuclear tests, accelerator experiments, and dedicated measurement satellites. By the 1980s, radiation hardening had become a mature discipline. Military satellites routinely incorporated shielding, redundant systems, and rad-hard electronics designed to survive both natural radiation and weapon effects. The techniques had been refined through decades of experience, informed by data from nuclear tests, accelerator experiments, and spaceflight measurements. Apollo's contribution was one element among many in this accumulated knowledge base. But for a critical period from 1969 through the mid-1970s, Apollo provided uniquely comprehensive measurements of radiation in cislunar space. During those years, America deployed the satellite constellations that would form the backbone of nuclear deterrence. Early warning systems, communication networks, reconnaissance platforms, all went operational during a period when Apollo data represented the most complete characterization of the deep space radiation environment. The strategic significance is difficult to quantify precisely. Would those satellites have worked without Apollo data? Almost certainly, engineers would have used conservative design margins, overbuilt the shielding, added redundancy, and relied on other data sources. But Apollo's measurements contributed to the body of knowledge that allowed more informed design decisions, potentially reducing weight and cost while maintaining reliability. This matters because satellite weight directly affects launch costs and mission capability. Every pound of shielding is a pound not available for sensors, fuel, or other payload. By contributing to better understanding of radiation protection requirements, Apollo data could enable optimization of the trade-off between hardening and capability. There is something worth reflecting on in this legacy. Apollo is remembered for flags and footprints, for Kennedy's challenge and Armstrong's words, for the triumph of exploration and the inspiration of achievement. All of that is real and important. But the program also produced data with applications beyond exploration, strategic implications that existed alongside the public narrative. The dosimeters the astronauts wore were measuring the space environment for stated scientific purposes. that the resulting data was publicly available and could inform military satellite design reflects the dual-use nature of Cold War technology development. Every reading, every particle track, every dose measurement contributed to knowledge that had multiple potential applications. This is not unique to Apollo. It is characteristic of how technology develops in contexts where civilian and military interests overlap. The lines between pure science and applied engineering, between exploration and strategy, are rarely as clean as popular narratives suggest. Apollo existed in that ambiguous space, genuinely advancing human knowledge while producing information relevant to broader strategic calculations. What makes Apollo's radiation measurements particularly interesting is how this dual nature has faded from popular memory. The dosimeters appear in mission reports. The data exists in technical papers. The potential military applications are a logical inference from the strategic context. None of it is classified. All of it is public. But the narrative of Apollo as pure exploration has dominated popular understanding. The truth is more complex and more interesting. Apollo was exploration and it existed within strategic context. It was science and it produced data with multiple applications. It was inspiration and it occurred during a period of intense nuclear competition. These dimensions do not diminish the achievement. They reveal the full complexity of what the program accomplished and the world in which it operated. Today, as new nations plan lunar missions and private companies promise cislunar commerce, the radiation environment remains a fundamental challenge. Modern electronics are in some ways more vulnerable than 1960s technology. Smaller transistors, higher densities, lower operating voltages all increase susceptibility to radiation effects. The data Apollo collected remains relevant because the physics has not changed. Cosmic rays still penetrate spacecraft. Heavy ions still disrupt electronics. The moon still lacks a magnetosphere. The next generation of lunar missions will carry sophisticated radiation monitors, far more capable than Apollo's passive dosimeters. They will measure particle fluxes with high temporal resolution, characterize radiation quality in detail, and provide real-time data for crew safety. But they will be building on a foundation established 50 years ago by astronauts who wore simple film badges and carried nuclear emulsion packs to the moon. Those measurements served the stated purpose of understanding astronaut health and the space environment. That they also contributed to knowledge with broader applications reflects the dual-use nature of technology in the Cold War era. Understanding this context does not diminish Apollo's legacy. It completes it, revealing the full complexity of achievement in an age when every frontier existed within larger strategic considerations and every mission occurred in a world of overlapping purposes. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
On July 9, 1962, at precisely 909 Coordinated Universal Time, a Thor rocket lifted off from Johnston Island carrying a weapon that would fundamentally alter the space environment surrounding Earth. The warhead was a W-49 thermonuclear device with a yield of 1.4 megatons. Its destination was not a target on the ground, but a point 250 miles above the Pacific Ocean. The detonation that followed lasted milliseconds. The consequences would persist for years. Starfish Prime, as the test was designated, was not an accident. It was not a miscalculation. It was a deliberate military experiment conducted at the height of the Cold War, designed to understand what would happen when nuclear weapons were detonated in the vacuum of space. The scientists and military planners who authorized it understood they were venturing into unknown territory. What they did not fully grasp was that they were about to cripple their own orbital infrastructure. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster. We focus on what was built, why it mattered, and where it really led. Now, back to the story. The flash from the detonation was visible across the Pacific. In Hawaii, 900 miles away, streetlights failed. Burglar alarms triggered spontaneously. Circuit breakers tripped across Honolulu. The electromagnetic pulse generated by the weapon had reached across nearly 1,000 miles of ocean to disrupt electrical systems on the ground. But the real damage was occurring where no one could see it. In the weeks and months following Starfish Prime, satellites began to fail. Not one or two, but 7 operational spacecraft, representing roughly 1/3 of all satellites then in orbit. Among them was Ariel 1, the United Kingdom's first satellite, launched just 4 months earlier. Its solar panels degraded rapidly. Its systems failed. By the end of the year, it was dead. The United States had just destroyed a significant portion of the very orbital infrastructure it was racing to build. To understand how this happened requires understanding what a nuclear detonation does in space. On the ground, the effects of a nuclear weapon are relatively well understood. Blast, heat, radiation, fallout. These effects are mediated by the atmosphere, which absorbs energy, creates shockwaves, and eventually brings radioactive particles back to Earth. In space, there is no atmosphere. There is no blast wave. There is no mushroom cloud. What remains are the fundamental products of nuclear fission and fusion, an expanding sphere of X-rays, gamma rays, neutrons, and charged particles, all moving at or near the speed of light. When Starfish Prime detonated at 250 miles altitude, those particles did not simply disperse into the void. They encountered Earth's magnetic field, and that changed everything. The magnetic field that shields Earth from solar radiation is not uniform. It is strongest near the poles and weakest near the equator. It extends tens of thousands of miles into space, creating a complex topology of field lines that trap and channel charged particles. This is what creates the Van Allen radiation belts, discovered just 4 years earlier by James Van Allen using data from Explorer 1. The electrons and other charged particles produced by Starfish Prime were captured by these magnetic field lines. They began to spiral along them, bouncing between the northern and southern magnetic poles, trapped in a new artificial radiation belt that would persist for years. The intensity of this artificial belt was extraordinary. Measurements taken in the months following the test showed radiation levels hundreds of times higher than the natural background. Satellites passing through this region were subjected to a continuous bombardment of high-energy electrons that no spacecraft of that era was designed to withstand. The damage mechanism was insidious. Solar panels, which convert sunlight to electricity using semiconductor materials, are particularly vulnerable to radiation. High-energy electrons passing through silicon create defects in the crystal lattice, reducing efficiency. Enough damage, and the panels stop functioning entirely. This is what happened to Ariel 1. Its solar panels degraded until they could no longer provide sufficient power to operate the spacecraft. But solar panel degradation was only one failure mode. The radiation also affected transistors and other electronic components, causing gradual performance degradation or catastrophic failure. Some satellites experienced immediate problems. Others died slowly over months, as cumulative radiation damage exceeded design tolerances. The casualties included Telstar 1, the first commercial communications satellite, launched just 1 day after Starfish Prime. It survived for several months but suffered progressive damage to its transistors and eventually failed in February 1963. Engineers at Bell Labs, who had designed and built Telstar, conducted extensive analysis and concluded that radiation from Starfish Prime had significantly shortened its operational life. The military satellites were not spared. Transit 4B, a Navy navigation satellite launched in 1961, failed in late 1962. Triac, an Air Force geodetic satellite, experienced power system problems. Engine 1, a scientific satellite from the University of Iowa, was damaged but managed to continue limited operations. The irony was profound. The United States had conducted Starfish Prime as part of Operation Fishbowl, a series of high-altitude nuclear tests intended to understand the effects of nuclear weapons in space. The strategic rationale was defensive. If the Soviet Union detonated nuclear weapons in orbit, American military planners needed to know what would happen to their reconnaissance satellites, communications networks, and early warning systems. What they discovered was that their own weapons were more dangerous to their own satellites than any plausible Soviet attack. The classified damage assessments that followed painted a grim picture. Internal documents from the Department of Defense and the Atomic Energy Commission, declassified decades later, reveal that the extent of the damage was understood almost immediately. Engineers and scientists tracking satellite performance could see the correlation between radiation levels and system failures. But this information was not made public. The British government, whose first satellite had been destroyed, was not officially informed that Starfish Prime was responsible. The failure of Ariel 1 was attributed to various technical problems. It was not until years later that declassified American documents confirmed what British scientists had suspected. Their satellite had been killed by radiation from an American nuclear test. The decision to proceed with Starfish Prime was not made lightly. It was the culmination of a series of high-altitude nuclear tests that had begun in 1958 with Operation Argus, which detonated 3 small nuclear weapons at altitudes between 100 and 300 miles. Those tests had demonstrated that artificial radiation belts could be created, but the weapons were small, yielding only 1 to 2 kilotons, and the effects were short-lived. Starfish Prime was different. At 1.4 megatons, it was roughly 1,000 times more powerful than the Argus devices. The weapon was large enough that its effects would be measurable, persistent, and strategically significant. That was precisely the point. Military planners wanted to know if high-altitude nuclear detonations could be used to create radiation barriers that would destroy enemy satellites or disrupt intercontinental ballistic missiles during their flight through space. The test was originally scheduled for June 20, 1962, but that attempt failed when the Thor rocket malfunctioned and had to be destroyed by range safety 59 seconds after launch. The warhead, still armed, fell into the ocean north of Johnston Island. A second attempt on July 9th succeeded. The detonation created a spectacle unlike anything seen before. The fireball, expanding in the vacuum of space, reached a diameter of several miles within seconds. Without atmospheric absorption, the X-rays and gamma rays from the weapon traveled unimpeded, creating an artificial aurora visible across the Pacific. Observers in Hawaii reported seeing red, white, and green lights in the sky, a phenomenon caused by the weapon's radiation-exciting atoms in the upper atmosphere. The electromagnetic pulse was equally dramatic. The burst of gamma rays from the weapon struck the upper atmosphere, knocking electrons free from air molecules. These electrons, accelerated by the weapon's electromagnetic fields, created a powerful current that generated a massive electromagnetic pulse. This pulse propagated along Earth's magnetic field lines, reaching the surface over a vast area. In Hawaii, the effects were immediate and widespread. Streetlights connected to series circuits failed when the surge damaged their controllers. A microwave relay station on Maui went offline. A telephone company switching station experienced multiple failures. The pulse had delivered a brief but intense surge of electrical energy that overwhelmed protective systems designed for lightning strikes and power surges. But these ground-level effects were transient and repairable. The damage in orbit was permanent. The artificial radiation belt created by Starfish Prime occupied a region of space between roughly 200 and 2,000 miles altitude, overlapping with the lower Van Allen belt and extending into regions where satellites routinely operated. The trapped electrons had energies ranging from hundreds of thousands to several million electron volts, high enough to penetrate spacecraft shielding and damage internal components. Measurements from surviving satellites equipped with radiation detectors showed that the intensity of the artificial belt initially exceeded the natural Van Allen belts by a factor of 100 or more in some regions. The decay rate was slower than expected. Models predicted the artificial belt would dissipate within months, but measurements showed it persisting for years. Detectable levels of radiation from Starfish Prime remained in orbit until the early 1970s, nearly a decade after the test. This persistence had profound implications for satellite design. Engineers could no longer assume that the radiation environment in low Earth orbit was benign or predictable. Spacecraft would need heavier shielding, radiation-hardened electronics, and larger safety margins in their power systems to account for solar panel degradation. All of this added mass, complexity, and cost. the Soviet Union conducted its own high-altitude nuclear tests during the same period. Between October 22 and November 1, 1962, the USSR detonated 5 nuclear weapons at altitudes between 90 and 180 miles as part of Operation K. These tests were smaller than Starfish Prime and conducted at lower altitudes, but they contributed additional radiation to the near-Earth environment. At least one Soviet satellite, Cosmos 3, failed shortly after these tests, suggesting that the Soviets had also damaged their own orbital infrastructure. The combined effect of American and Soviet high-altitude nuclear tests was to create an artificial radiation environment in low Earth orbit that would persist for years and fundamentally alter the trajectory of satellite development. The space age, barely 5 years old, had already been contaminated by the weapons of the Cold War. The political response was swift but incomplete. In August 1963, the United States, Soviet Union, and United Kingdom signed the Partial Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, outer space, and underwater. The treaty was motivated by multiple concerns, including radioactive fallout from atmospheric tests and the growing recognition that high-altitude tests posed risks to satellites. But the treaty did not undo the damage. The artificial radiation belts created by Starfish Prime and the Soviet K tests remained in orbit, continuing to pose hazards to spacecraft. And the treaty's prohibition on space-based nuclear tests was not absolute. It contained no verification provisions and relied on national technical means of detection. Underground nuclear tests, which could not be reliably detected, were permitted to continue. The classified assessments of Starfish Prime's effects on satellites were not fully declassified until the 1990s, more than 3 decades after the test. When researchers finally gained access to these documents, they revealed the extent to which military planners had underestimated the risks. Internal memos showed that while scientists had predicted some satellite damage, the actual casualty rate exceeded expectations. The artificial radiation belt was more intense, more persistent, and more geographically extensive than models had predicted. One particularly revealing document was a 1963 report from the Defense Atomic Support Agency analyzing the failure of military satellites following Starfish Prime. The report concluded that the test had significantly degraded American reconnaissance and communications capabilities in orbit and recommended against future high-altitude nuclear tests unless absolutely necessary for national security. The recommendation was accepted. The United States never again detonated a nuclear weapon in space. But the damage to international relations was harder to repair. The destruction of Ariel 1, Britain's first satellite, occurred at a time when the UK was working to establish itself as a spacefaring nation. The satellite had been launched as part of a collaborative agreement with NASA, with British scientists providing the instruments and American rockets providing the launch. Its premature failure was a setback for the British space program and a source of friction in the Anglo-American relationship. British scientists suspected almost immediately that Starfish Prime was responsible for Ariel 1's demise. The timing was too coincidental. The satellite had been functioning normally until shortly after the test, then began experiencing power problems consistent with solar panel damage. But without access to American data on the artificial radiation belt, they could not prove it. And American officials were not forthcoming. It was not until 1968, 6 years after the test, that American scientists published detailed measurements of the Starfish Prime radiation belt in the open literature. By then, the artificial belt had decayed significantly but was still detectable. British scientists used this data to model the radiation dose received by Ariel 1 and confirmed that it had been lethal to the spacecraft's solar panels. The legacy of Starfish Prime extends beyond the satellites it destroyed. The test demonstrated that the space environment could be weaponized, that orbital infrastructure was vulnerable, and that the consequences of space-based weapons could be unpredictable and long-lasting. These lessons informed subsequent arms control negotiations and shaped the development of space law. The Outer Space Treaty of 1967 prohibited the placement of nuclear weapons in orbit and banned military bases on celestial bodies, but it did not prohibit all military uses of space. Reconnaissance satellites, communication satellites, and navigation satellites remained permissible. The treaty represented a compromise between the desire to prevent the weaponization of space and the recognition that space had become essential to national security. But the treaty's prohibitions were never absolute. Anti-satellite weapons continued to be developed and tested by multiple nations. In 1985, the United States demonstrated an air-launched anti-satellite missile that destroyed a satellite in low Earth orbit. In 2007, China conducted a similar test, destroying one of its own weather satellites and creating a debris field that remains a hazard to other spacecraft. In 2019, India joined the club with its own anti-satellite test. Each of these tests created debris. Each posed risks to other satellites. And each demonstrated that orbital infrastructure remains vulnerable to attack. The lesson of Starfish Prime, that weapons in space can damage friendly assets as easily as enemy ones, has not been fully internalized. The technical challenges revealed by Starfish Prime also had lasting effects on satellite design. Modern spacecraft operating in regions affected by radiation must incorporate extensive protective measures. Electronics are radiation-hardened through careful selection of materials and circuit designs that are resistant to single-event upsets and cumulative damage. Solar panels use materials and coatings designed to minimize degradation. Shielding is added to protect sensitive components. All of this adds mass and cost. A satellite designed to operate in a high-radiation environment can weigh significantly more than one designed for a benign orbit. For missions to geostationary orbit, which pass through the Van Allen belts during ascent, or for missions to high-inclination orbits that spend extended time in the radiation belts, these design considerations are unavoidable. The artificial radiation belt, created by Starfish Prime, also provided an unintended scientific benefit. It served as a natural laboratory for studying radiation belt dynamics, particle transport, and the interaction between charged particles and Earth's magnetic field. Data from satellites equipped with radiation detectors allowed scientists to track the decay of the artificial belt and refine their models of how particles are trapped and lost from the magnetosphere. These studies revealed that the decay of the artificial belt was driven by multiple processes. Some electrons were scattered into the atmosphere by interactions with atmospheric molecules at the lower boundary of the belt. Others were lost through wave-particle interactions, where electromagnetic waves in the magnetosphere transferred energy to the electrons and knocked them out of their trapped orbits. Understanding these processes improved predictions of natural radiation belt behavior and helped engineers design better shielding for spacecraft. But the scientific value of Starfish Prime does not excuse the decision to conduct the test. The damage to operational satellites, the contamination of the near-Earth environment, and the risks to future space activities were real and significant. The test represented a failure of foresight, a willingness to experiment with systems whose behavior was poorly understood, and a prioritization of military objectives over the nascent international space program. The decision-makers who authorized Starfish Prime were not reckless. They consulted with scientists, reviewed models, and attempted to predict the consequences. But they were operating in an environment of profound uncertainty. The Van Allen belts had been discovered only 4 years earlier. The behavior of nuclear weapons in space was largely theoretical. The vulnerability of satellites to radiation was not well characterized. In this context, they chose to proceed, accepting risks they did not fully understand. This pattern would repeat throughout the Cold War. Technologies were deployed, weapons were tested, and systems were built without complete knowledge of their long-term consequences. The space environment became a testing ground for military capabilities, and the costs were borne by everyone who relied on orbital infrastructure. Today, thousands of satellites orbit Earth. They provide communications, navigation, weather forecasting, Earth observation, and scientific research. The global economy depends on them. Modern life would be unrecognizable without them. And all of them remain vulnerable to the same threats demonstrated by Starfish Prime: radiation, electromagnetic pulses, and the weaponization of space. The artificial radiation belt, created in 1962, has long since decayed. The last detectable traces disappeared in the early 1970s. But the precedent remains. We know that nuclear weapons can create artificial radiation belts. We know that these belts can destroy satellites. And we know that the effects can persist for years. In an era of renewed great power competition, with multiple nations developing anti-satellite weapons and demonstrating capabilities in space, the lessons of Starfish Prime are more relevant than ever. The orbital infrastructure we depend on is fragile. The space environment can be weaponized, and the consequences of conflict in space will not respect national boundaries or political allegiances. Starfish Prime was not a failure of technology. The weapon worked exactly as designed. It was a failure of judgment, a miscalculation of consequences, and a demonstration that even sophisticated military planners can underestimate the complexity of the systems they seek to control. The satellites it destroyed were not enemy assets. They were our own, and those of our allies, casualties of an experiment that revealed how little we understood about the environment we were beginning to inhabit. The tragedy is not just what was lost, but what was revealed. That the rush to weaponize space outpaced the wisdom to understand it, and that the infrastructure we were building could be destroyed as easily by our own actions as by any adversary. In the vacuum above Earth, where there is no atmosphere to absorb mistakes and no borders to contain consequences, we learned that every weapon is pointed at ourselves.
In 1958, in a classified meeting room at Kirtland Air Force Base in New Mexico, Air Force officers posed a question to assembled scientists that sounds like the fever dream of a science fiction writer. What would it look like if we could blow up the moon? This wasn't a thought experiment. This wasn't idle speculation over coffee. This was Project A119, a top-secret plan to detonate a nuclear weapon on the lunar surface, creating an explosion visible to every human being on Earth. The ultimate Cold War flex. A mushroom cloud rising above humanity's ancient celestial companion, backlit against the darkness of space. And a brilliant 24-year-old graduate student named Carl Sagan, decades before he'd become the world's most beloved voice of cosmic wonder, helped calculate exactly how to make it happen. The beeping of Sputnik wasn't just a radio signal. It was a psychological weapon that rewired the American psyche overnight. October 4th, 1957. That's the date everything shattered. When Sputnik launched, crossing American skies every 96 minutes, it didn't just mark a Soviet technological achievement. It triggered an existential crisis that gripped the nation by its throat. Amateur radio operators across the country could tune in and hear it. Beep, beep, beep. A mechanical taunt from 560 miles overhead, a constant reminder that the enemy had seized the high ground. For Americans listening to that Soviet satellite pass overhead, each beep felt like a countdown to annihilation. If the Soviets could put a satellite in orbit, what else could they do? Launch nuclear weapons from space? Establish military bases on the moon? Rain down destruction on American cities with no warning, no defense, no hope? The fear wasn't abstract. It was visceral, immediate, and it demanded a response that would be equally spectacular. Newspapers ran apocalyptic headlines. Congressional hearings devolved into panic. Military strategists scrambled for answers. The United States, the nation that had split the atom, that had won World War II, that considered itself the undisputed technological champion of the free world, had been humiliated by a beach ball-sized sphere of metal and radio transmitters. Within months, under immense pressure to restore American prestige and reassure a terrified public, the U.S. Air Force's Special Armament Center initiated something extraordinary. In May 1958, they contracted the Armor Research Foundation at the Illinois Institute of Technology for what they officially called a study of lunar research flights. The vague title was deliberate, bureaucratic camouflage designed to obscure the project's true purpose. Its real designation was Project A119. And its goal wasn't exploration or scientific advancement. It was to study the feasibility of detonating a nuclear weapon on the moon's surface, creating a display of American technological might that would be visible from Earth 240,000 miles away. A cosmic fireworks display powered by the same force that had leveled Hiroshima. This wasn't about military advantage. It was about theater. Pure psychological warfare dressed up in the language of scientific inquiry. A Cold War chess move designed to demoralize the Soviets and reassure Americans, regardless of the consequences. The question wasn't whether America should nuke the moon. The question was whether they could, and how spectacular it would look when they did. Imagine being a respected physicist, focused on legitimate research, and your phone rings with a classified commission that sounds like it was dreamed up by a committee of comic book villains and desperate generals. That was Dr. Leonard Reifel's introduction to Project A119. Within months of Sputnik's launch, a small team of scientists in Chicago received a classified assignment that would push the boundaries of both physics and sanity. Their mission: figure out how to detonate a nuclear bomb on the moon and make sure the whole world could see it. Dr. Leonard Reifel, a 34-year-old physicist at the Armor Research Foundation, became the project's lead scientist. He was a pragmatist, a serious researcher who found himself coordinating a study that blended cutting-edge physics with Cold War absurdity. Later, he would describe the atmosphere as driven by an intense sense of urgency, with a lot of pressure to come up with something spectacular. This wasn't a panel of mad scientists cackling over destruction. These were serious researchers, astronomers, physicists, engineers, suddenly tasked with answering questions no one had ever needed to ask before. How high would a mushroom cloud rise in 1/6 gravity? How would nuclear fire behave in a vacuum? Could you hit a moving target 240,000 miles away with 1950s guidance systems? To answer these impossible questions, Reifel assembled a small elite team. Among them was a brilliant graduate student whose theoretical work on lunar dust and the moon's exosphere would prove crucial to determining whether this audacious plan could actually work. His name was Carl Sagan. In 1958, Sagan was just beginning his career, a young, ambitious astronomer eager to make his mark in the emerging field of planetary science. His assignment? Calculate how visible the explosion would be from Earth. Model the behavior of lunar dust in vacuum conditions. Determine if a nuclear detonation 240,000 miles away could create a spectacle that would restore American pride and Soviet fear. It was, in retrospect, a darkly ironic introduction to space science for someone who would spend his career advocating for the peaceful exploration of the cosmos. As the team dug into the calculations, they identified the optimal weapon, the W-25 warhead, a relatively small tactical nuclear device with a yield of 1.7 kilotons. To put that in perspective, it was roughly 1/10 the power of the bomb that destroyed Hiroshima, small enough to be manageable with existing rocket technology, but still powerful enough to produce a visible explosion from Earth. The delivery system would be a modified Atlas or Titan intercontinental ballistic missile, the same rockets being developed to reach escape velocity, and with the right modifications, capable of delivering payloads across lunar distances. These were cutting-edge machines, barely proven, now being repurposed to strike not Soviet cities, but the face of the moon itself. And the target? The lunar terminator, the line between day and night on the moon's surface. Detonate the bomb there, and the explosion's dust plume would be backlit against the darkness, illuminated by the sun, maximizing visibility from Earth for maximum propaganda impact. Reifel's calculations showed the plan was technically feasible. The technology existed. The physics checked out. But as he produced his comprehensive feasibility study, a crucial caveat appeared in his report, a single sentence that revealed the growing unease in his conscience. I made it clear that my report was a feasibility study only and did not reflect my personal endorsement of the idea. It was a scientist's quiet rebellion, a way of saying we can do this while carefully not saying we should. Here's the challenge with nuking the moon. While it lacks a substantial atmosphere, the explosion was still predicted to create a cloud rising several kilometers above the surface, although less defined and quicker to dissipate than a mushroom cloud on Earth. So how do you make that visible across 250,000 miles of space? The answer required Carl Sagan to solve problems no human had ever confronted. Picture this. You're a 24-year-old graduate student, excited about studying the cosmos, and your assignment is to calculate the visibility of a nuclear mushroom cloud on the moon. Not the atmospheric composition of Venus, not the rings of Saturn. The optimal detonation point for a weapon of mass destruction on another world. Sagan approached the project with the same rigor he'd later bring to his groundbreaking work on planetary atmospheres. His calculations had to account for factors that existed only in theory. The moon's surface composition was largely unknown. Was it solid rock? Loose dust meters deep? How would the vacuum of space affect the explosion dynamics? How would 1/6 gravity influence the debris plume? He determined that the explosion would create a massive plume of lunar dust and debris. In Earth's atmosphere, a nuclear detonation creates that iconic mushroom shape through the interaction of the fireball with air molecules. On the moon, the physics would be radically different. The initial flash would be brilliant but brief. The real spectacle would come from the dust. Tons of pulverized lunar regolith hurled upward by the blast, creating a cloud that would rise several kilometers above the surface. And if timed correctly, detonated at the lunar terminator where sunlight could illuminate the expanding dust cloud against the darkness, Sagan's calculations suggested it would be visible to the naked eye from Earth. A cosmic firework 240,000 miles away. A brief, brilliant flash followed by an expanding plume. A monument to human technological prowess and hubris visible to every person who looked up at the night sky. When Sagan presented these findings to the Air Force sponsors, witnesses described what Leonard Riefel later called a eureka moment. The brass saw their propaganda victory materializing in equations and trajectory plots. It could actually work. But here's what haunted the project. They were operating on speculation and untested assumptions. In 1958, humanity had virtually no direct data about the lunar surface. Every calculation about how the regolith would react, how the dust would disperse in vacuum, how the plume would behave in 1/6 gravity, all of it was theoretical. Educated guesses based on telescope observations and physics models that had never been tested beyond Earth. The delivery mechanism presented its own nightmare of precision engineering, hitting a target 384,400 kilometers away with guidance systems that had barely mastered Earth orbit required accuracy within a few kilometers across the void of space. The warhead and its electronics had to survive cosmic radiation levels no nuclear device had ever faced. Temperature extremes ranging from 127 degrees Celsius in lunar sunlight to negative 173 degrees Celsius in shadow. And there would be no mid-course correction, no second chance if the calculations were off by even a fraction of a degree. They were adapting weapons of mass destruction for a mission profile that existed only on paper, using computers less powerful than a modern smartphone to calculate trajectories that would make history, or become the most visible failure in human history. The team produced a comprehensive 190-page classified report detailing the technical feasibility, the optimal detonation point, the expected visibility, the delivery systems. On paper, Project A119 could work. But as the scientists dug deeper into their own calculations, as the initial excitement gave way to sober reflection, a different kind of problem emerged. One that no amount of mathematics could solve. There's a moment in every ambitious project when someone asks the question no one wants to hear. Should we actually do this? For Project A119, that moment came when scientists realized they might be about to turn humanity's greatest symbol of wonder into a radioactive wasteland, and call it progress. Leonard Reifel saw it first. As the project's lead scientist, he'd assembled the calculations, mapped the trajectories, proven the concept worked. The science was sound. The technology existed. But in his final report to the Air Force, that crucial caveat appeared. His way of handing the military a loaded gun while making it clear he wouldn't pull the trigger himself. Carl Sagan, the brilliant young theorist whose calculations had proven the explosion would be visible from Earth, raised more direct concerns. What about radioactive contamination of the lunar surface? The explosion would scatter radioactive isotopes across the impact site. Strontium-90, cesium-137, plutonium, elements that would remain hazardous for decades, perhaps centuries. What happens when the public finds out we've poisoned the moon? His questions weren't hypothetical. They were warnings about turning a propaganda victory into a scientific and public relations disaster. Declassified documents reveal the internal debates that followed. Scientists worried about contaminating the moon for future scientific exploration. The very dust they'd planned to illuminate with nuclear fire would carry radioactive isotopes across the lunar surface, potentially destroying irreplaceable scientific data about the moon's formation and the early solar system. Humanity's first extraterrestrial destination would arrive pre-poisoned, a cosmic crime scene of our own making. But beyond the scientific concerns, a more immediate fear gripped military planners: the spectacular potential for catastrophic, globally witnessed failure. Think about it. The project sold as demonstrating American technological superiority could become the ultimate embarrassment. Missing the moon entirely, the missile sailing past into deep space while the world watched, would be humiliating. But worse would be a dud, a warhead that failed to detonate, creating nothing but silence and darkness. While Soviet propaganda machines worked overtime, America's grand gesture reduced to a cosmic whimper, broadcast globally, immortalized in failure. And then there was the international backlash to consider. If the plan leaked before execution, or succeeded and triggered global outrage, America would be seen as recklessly militarizing space, turning the cosmos into a battlefield. The propaganda victory would evaporate in the face of worldwide condemnation. By January 1959, less than a year after its inception, Project A119 was quietly shelved. No official announcement, no explanation, no dramatic cancellation order. Just a classified report filed away in a secure facility and a small team of scientists reassigned to other projects. Multiple factors contributed to the decision. Military advisors recognized the public relations nightmare. Scientists, including Reifel himself, argued that contaminating the moon would destroy irreplaceable scientific opportunities. The technical risk of visible failure loomed large. And perhaps most importantly, there was a growing recognition that weaponizing space could trigger a dangerous new phase of the arms race, with both superpowers turning the cosmos into a battlefield. The project remained classified for nearly 40 years. Then, in 2000, Leonard Reifel revealed its existence in interviews with the press, shocking historians and the public alike. The revelation came with a footnote that made headlines. Carl Sagan, the beloved astronomer who had spent his career advocating for the peaceful exploration of space, who had written Cosmos and Pale Blue Dot, who had become humanity's greatest cosmic storyteller, had once calculated how to make a nuclear explosion on the moon visible from Earth. There was another twist to Sagan's involvement. In his graduate school applications, the young scientist had mentioned the classified project, violating security protocols in his enthusiasm to showcase his work. It was a mistake that could have derailed his career before it began. A youthful indiscretion that nearly cost him everything. But perhaps the ultimate revelation was this. Project A119's cancellation wasn't a failure. It was one of the Cold War's rare moments of collective sanity. Scientists, military planners, and political leaders all stepped back from the brink, recognizing that some demonstrations of power are too dangerous to contemplate, even in an era defined by nuclear brinkmanship and existential fear. In the end, Project A119 died. Not with a bang, but with a bureaucratic whimper. And that quiet death may be one of the most important decisions our species has ever made. The Air Force ultimately judged the risks, scientific, technical, and reputational, as outweighing any potential benefits. The concerns Rifle had voiced about contaminating the moon for future exploration, about the potential for catastrophic failure broadcast globally, had won out. The reports were filed away, classified, and the scientists moved on to other work. The moon remained untouched, unmarked by human weapons, pristine as it had been for 4 billion years. For decades, Project A119 remained one of the Cold War's buried secrets, a footnote in classified files that few would ever read. But its legacy lived on in ways its creators never anticipated. The ethical debates it sparked, about contaminating celestial bodies, about the militarization of space, about the line between technological capability and moral responsibility, directly influenced the Outer Space Treaty of 1967. This landmark agreement, signed by the United States, the Soviet Union, and dozens of other nations, banned nuclear weapons and weapons of mass destruction on the moon and other celestial bodies. It established space as a realm for peaceful exploration, not military conquest. Where once nations considered spectacular shows of force, they now negotiated treaties and cooperation. Where Cold War paranoia had pushed scientists to calculate mushroom cloud heights on alien worlds, a new generation would work together on joint missions, shared data, and collaborative science. Today, as we prepare to return to the moon through the Artemis program, as we plan permanent lunar bases and use the moon as a stepping stone to Mars, we do so under the principles established by that treaty, a direct descendant of the ethical awakening that killed Project A119. The moon remains untouched by nuclear weapons, a testament to a moment when fear almost drove us to irreversible action. When you look up tonight and see the moon hanging in the darkness, its face marked only by the ancient craters of cosmic impacts, not the fresh scars of human weapons, you're witnessing the result of a choice made in a moment of Cold War madness, and ultimately rejected. Project A119 stands as a reminder that in the space race, sometimes the most important victories are the disasters we avoid. The question those Air Force officers asked, "What would it look like if we could blow up the moon?" was answered not with a mushroom cloud, but with restraint. The cosmos is vast, ancient, and indifferent to our fears. But it's also ours to explore, not to destroy. And that choice, made by scientists who found their conscience, by military planners who recognized the limits of power, by a nation that stepped back from the brink, may be one of the most profound acts of wisdom in human history. Sometimes the most powerful thing we can do is choose not to pull the trigger. The moon still hangs in our sky, not as a battlefield or a propaganda target, but as it always was. A symbol of wonder, a destination for dreamers, and a reminder that our reach into the cosmos should be guided not by fear, but by the better angels of our nature. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
In 1964, NASA engineers were designing something remarkable. Not a flag-planting mission, not a brief sortie to collect rocks and leave footprints. They were planning permanent human habitation on the moon, powered by compact nuclear reactors that would hum quietly in the lunar regolith, generating kilowatts of continuous power for years without refueling. The lunar exploration system for Apollo, known as LISA, represented the logical next step after the initial Apollo landings. While Kennedy's challenge focused the nation on reaching the moon before the decade ended, NASA's long-range planners were already thinking beyond that first boot print. They envisioned extended surface operations, mobile laboratories traversing hundreds of kilometers, and habitats that could sustain crews for months at a time. All of this required power, substantial and reliable power, far beyond what solar panels or fuel cells could provide in the harsh lunar environment. The numbers told the story. A basic Apollo lunar module carried enough battery and fuel cell capacity for perhaps 75 hours on the surface. The LISA concept called for 14-day missions initially, extending to 30 days and eventually 90-day stays. The power requirements scaled accordingly. Life support systems, environmental controls, scientific instruments, communication arrays, and the mobility systems needed to make extended exploration worthwhile. All of this demanded kilowatts, not watts. Solar panels presented problems. The lunar day lasts 14 Earth days, followed by 14 days of darkness at temperatures approaching -170 degrees Celsius. Battery storage for 2 weeks of night operations was impractical with 1960s technology. The mass alone would have required multiple Saturn V launches just to deliver the power system. Nuclear reactors offered an elegant solution. Compact, reliable, indifferent to day or night, capable of operating for years with no moving parts in the primary system. The Atomic Energy Commission had been developing space reactor technology since the late 1950s under the SNAP program, Systems for Nuclear Auxiliary Power. By 1964, several reactor designs existed that could theoretically meet NASA's requirements. SNAP-10A had already flown in space, the first and only U.S. nuclear reactor to operate in orbit, generating 500 watts for 43 days in 1965 before a non-nuclear system failure ended the mission. More powerful designs were on the drawing boards. The MOLAB concept emerged from this planning environment. The Mobile Lunar Laboratory was not a small rover like the later lunar roving vehicle that flew on Apollo 15, 16, and 17. MOLAB was a truck-sized pressurized vehicle, a habitat on wheels that could travel hundreds of kilometers from the landing site while maintaining shirt-sleeve environment for a crew of 2. The design studies showed a vehicle roughly 6 meters long, 3 meters wide, mounted on large wire mesh wheels that could navigate the boulder fields and crater slopes that defined much of the lunar terrain. Inside, the crew would have bunks, a small galley, waste management facilities, and a comprehensive suite of scientific instruments. The vehicle would serve as both transportation and temporary base, allowing geological surveys far beyond the range of a suited astronaut on foot. Power requirements for MOLAB were substantial. The life support system alone needed several kilowatts continuous. Heating during the lunar night, cooling during the day, communications, navigation, the science package. All of these systems drew power constantly. The mobility system, whether electric motors or some hybrid arrangement, demanded even more during transit. Early studies suggested a minimum of 10 kilowatts, with 15 to 20 kilowatts preferred for operational flexibility. No battery technology of the era could provide this for the planned mission durations. Solar panels would have worked during the lunar day but required the vehicle to remain stationary during the 2-week night or carry impossible amounts of battery storage. A small nuclear reactor, perhaps derived from SNAP-8 or a similar design, seemed like the only viable option. The base habitat designs went further. LISA planning documents from 1964 and 1965 describe modular structures that could be landed separately and assembled on the surface. These weren't the small shelters of Apollo. They were laboratory complexes with dedicated areas for geology, biology, astronomy, materials science, and medical research. Power requirements ranged from 25 to 50 kilowatts, depending on the configuration and crew size. Some designs called for multiple reactors, providing redundancy and allowing maintenance on one unit, while others continued operation. The reactors would be buried in the regolith, both for radiation shielding and thermal management, with only power cables running to the habitat modules. This is where the story takes its dark turn. Because while NASA engineers were calculating power budgets and habitat volumes, while contractors were designing reactor mounting systems and radiation shields, while the agency was committing these plans to paper and presenting them to Congress, they were missing critical information. Information that existed, that had been measured and characterized in extensive testing programs, but information they could not access because of classification barriers erected by the Atomic Energy Commission and the Department of Defense. The problem was not that space reactor technology was classified. NASA had clearances. The agency worked closely with the AEC on nuclear propulsion studies, on reactor designs, on the basic physics and engineering. The problem was more subtle and more damaging. The detailed hazard data, the precise measurements of radiation release during accident scenarios, the contamination studies showing exactly what would happen if a reactor failed during launch or landing. This information existed in classified test reports that NASA was not permitted to see. Understand what this meant in practical terms. NASA engineers needed to know how much shielding to place between a reactor and the crew habitat. This is not a simple calculation. It depends on the reactor design, the fuel type, the power level, the geometry of the installation, and critically, on what happens when things go wrong. A reactor operating normally produces a known radiation field that can be shielded with understood amounts of material. But a reactor that has experienced a coolant leak or a control failure or physical damage during landing, that reactor might produce very different radiation signatures. It might release volatile fission products. It might experience localized power excursions. The shielding requirements could change dramatically. The AEC had conducted extensive testing on these failure modes. They had deliberately destroyed test reactors under controlled conditions to measure what happened. They had characterized the release of cesium-137, strontium-90, iodine-131, all the nasty fission products that make reactor accidents dangerous. They had measured gamma-ray spectra, neutron fluxes, contamination patterns. This data existed. It sat in file cabinets at Los Alamos, at Sandia, at the National Reactor Testing Station in Idaho. But it was classified, not because of the reactor designs themselves, but because the failure mode analysis revealed information about nuclear weapons effects. The connection was not obvious, but it was real. Understanding how fission products disperse from a damaged reactor core requires understanding blast physics, thermal effects, and radioactive transport mechanisms that are identical to the physics of nuclear weapons fallout. The models used to predict contamination from a reactor accident were derived from weapons test data. The measurement techniques, the instrumentation, the analysis methods, all of this technology had dual-use implications. So it was classified, buried behind security barriers that prevented NASA engineers from accessing it, even though they had legitimate need and appropriate clearances. This created an impossible situation. NASA was planning to place nuclear reactors on the moon, devices that would be launched on rockets, landed on an airless body with 1/6 Earth's gravity, operated remotely or in close proximity to crew, and potentially abandoned in place when missions ended. Every one of these operations carried risk. A launch failure could scatter reactor fuel across the Atlantic. A landing accident could breach the reactor vessel and contaminate the landing site. A coolant failure during operations could expose the crew to radiation. An abandoned reactor could become a hazard for future missions to the same region. NASA needed to quantify these risks, to design mitigation measures, to prove to Congress and the public that the benefits justified the dangers. But they could not do this properly without the hazard data. They could make conservative assumptions, and they did. They could use unclassified reactor physics codes to estimate radiation fields, and they did. They could design shielding based on worst-case scenarios, and they did. But they could not perform the detailed safety analysis that the mission actually required. They could not tell Congress with confidence how deep to bury the reactor because they did not have access to the contamination dispersion models. They could not specify crew shielding mass with precision because they did not know the exact spectrum of radiation that would emerge from various failure scenarios. They could not plan emergency procedures because they did not understand the timeline of a reactor accident in lunar conditions. The burial depth question was particularly vexing. Lunar regolith provides excellent radiation shielding. It is effectively rock powder, dense and uniform, and a few meters of it will stop most radiation. But how much was needed? The answer depended on the reactor design, the power level, and critically, on whether the reactor was operating normally or had experienced some failure. An operating reactor might need 2 meters of overburden. A damaged reactor leaking fission products might need 5 meters or 10, or might contaminate the regolith so thoroughly that burial was pointless. NASA did not know because the AEC would not share the data. The contamination studies were equally problematic. The moon has no atmosphere, no weather, no rain to wash away contamination. Radioactive material released on the lunar surface would remain there, effectively forever, moved only by micrometeorite impacts and the slow gardening effect of cosmic ray bombardment. A reactor accident could render a large area unusable for future missions. But how large? What isotopes would be present? How would they distribute in the regolith? What radiation levels would persist after a year, a decade, a century? The AEC had studied these questions in the context of nuclear weapons effects on Earth. The models existed. The data existed. NASA could not see it. By 1966, the LISA program was running into serious trouble. The technical challenges were mounting, the costs were escalating, and the safety questions remained unanswered. NASA tried to work around the classification barriers. They commissioned their own studies using unclassified data. They hired contractors with appropriate clearances to perform analyses using classified information and deliver sanitized results. They negotiated with the AEC for access to specific data sets. None of this worked well. The unclassified studies were too conservative, predicting shielding requirements so large that the reactor systems became impractical. The contractor studies delivered conclusions without the supporting data, making it impossible for NASA engineers to verify the results or adapt them to design changes. The AEC negotiations moved slowly, bogged down in bureaucratic processes, and genuine security concerns. The political environment was shifting as well. The Apollo program was consuming enormous resources. The Vietnam War was escalating, draining federal budgets and public attention. The initial enthusiasm for space exploration was fading as the reality of costs became clear. Congress was asking harder questions about NASA's long-range plans. The moon-based concepts, with their nuclear reactors and extended missions and multi-launch architectures, looked expensive and risky. Without solid safety data, NASA could not make a convincing case that the risks were manageable. MOLAB died quietly in 1967. The program was not canceled in any dramatic fashion. It simply faded from planning documents, replaced by more modest concepts that did not require nuclear power. The lunar roving vehicle that eventually flew was battery-powered, limited to a few kilometers range, operated only during the lunar day. It was a useful vehicle, but nothing like the mobile laboratory that had been envisioned. The LISA program lingered a bit longer, gradually shrinking in scope until it too disappeared, absorbed into the general post-Apollo planning that never quite materialized into hardware. The SNAP reactor program continued, but without a clear mission. SNAP-10A remained the only U.S. reactor to operate in space. More advanced designs were tested on the ground, but never flew. The AEC built and tested SNAP-8, a 35-kilowatt reactor intended for space applications, but no spacecraft ever used it. The technology worked, the engineering was sound, but without NASA missions to fly them, the reactors had no purpose. By the early 1970s, the space reactor program was essentially dead, kept alive at minimal funding levels as a hedge against future needs that never arrived. The Soviet Union faced similar challenges but responded differently. They flew dozens of nuclear reactors in space, primarily for radar reconnaissance satellites that needed more power than solar panels could provide in low Earth orbit. The Roarsat program operated from 1967 to 1988, launching 33 reactor-powered satellites. Several failed, including Cosmos 954, which crashed in northern Canada in 1978, scattering radioactive debris across hundreds of kilometers. The Soviets never attempted a lunar reactor, but they demonstrated that space nuclear power was technically feasible if you were willing to accept the risks. The classification barrier that hampered NASA in the 1960s was not unique to that era. It reflects a fundamental tension in nuclear technology development. Information about nuclear systems is inherently dual use. The physics of reactor safety overlaps with the physics of weapons effects. The engineering of radiation shielding applies equally to protecting spacecraft crews and hardening military systems against nuclear attack. The contamination models that predict fallout from a reactor accident derive from weapons test data. This creates situations where civilian agencies need information that exists in classified military programs but cannot access it without compromising security. The problem persists today. Current plans for lunar bases and Mars missions include nuclear power systems. NASA is developing the kilopower reactor, a small fission system designed to provide 10 kilowatts for surface operations. The technical challenges are similar to those faced by LISA planners in the 1960s. The safety questions are the same. And while the classification environment has changed somewhat, barriers still exist. Some information remains restricted. Some analysis tools are not available to civilian engineers. The lessons of the 1960s have been partially learned, but the underlying tensions remain. What makes this story particularly frustrating is the waste. The technology existed. The engineering was sound. NASA had capable engineers and adequate budgets, at least initially. The AEC had the safety data. The information was there, sitting in file cabinets, unavailable because of security classifications that may or may not have been necessary. We will never know if the LISA program would have succeeded if NASA had full access to the hazard data. Perhaps the safety challenges would have proven insurmountable anyway. Perhaps the costs would have killed the program regardless. But we do know that the classification barriers prevented a proper attempt. They forced NASA to plan in ignorance, to make decisions without adequate information, and ultimately to abandon concepts that might have worked. The alternative history is tantalizing. Imagine MOLAB traversing the lunar highlands in 1972, its reactor humming quietly beneath the regolith, its crew exploring regions that remain unvisited to this day. Imagine a permanent base at the lunar South Pole, powered by multiple SNAP reactors, operating continuously through the long lunar night, supporting scientific research that could not be done any other way. Imagine the engineering knowledge gained from operating nuclear systems in space, The confidence built through successful missions, the foundation laid for more ambitious ventures to Mars and beyond. All of this was possible with 1960s technology. All of it was planned, at least in preliminary form. None of it happened, in part because the people who needed to know could not access what others had learned. This is not a story about technical failure. The reactors worked, the designs were viable. This is a story about institutional failure, about the ways that security classifications and bureaucratic boundaries can strangle innovation. It is a story about the cost of secrecy, measured not in dollars, but in lost opportunities and abandoned dreams. The nuclear moon base was not science fiction. It was engineering, solid and achievable, killed by information barriers that served no clear purpose and protected no vital secret. Today, the plans sit in archives. The LISA documents are declassified now, available to anyone who cares to request them. The MOLAB designs can be found in NASA technical reports from the 1960s. The SNAP reactor test data, at least some of it, has been released. You can read about the missions that were planned, the hardware that was designed, the future that was imagined and then discarded. The information is there, too late to matter, too late to save the programs it might have enabled. The reactors that could have powered lunar bases were tested and proven, then shelved when the missions disappeared. The mobile laboratories that could have explored the moon remain paper studies, occasionally rediscovered by new generations of engineers who briefly wonder why we gave up on such capable systems before flying them even once. The lesson, if there is one, is about the fragility of ambitious programs. They require not just technology and funding, but also information, access, and institutional cooperation. When any of these elements fails, the entire enterprise can collapse, leaving behind only documents and photographs and the lingering question of what might have been. The nuclear moon base was real, at least on paper. It could have been built. It could have worked. That it was not tells us something important about how we make decisions, how we handle information, and how easily we abandon difficult goals when obstacles appear. The moon is still there, still airless and cold, still waiting for the permanent human presence that was planned 6 decades ago. The reactors that could have powered that presence exist in museums now, or in storage, or were dismantled long ago. The knowledge remains, scattered and incomplete, a testament to the missions we chose not to fly and the future we decided not to build. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
July 20th, 1969. Neil Armstrong plants an American flag on the moon, a symbol of peaceful exploration. But rewind 10 years, and that flag could have been surrounded by something far more sinister. In 1959, while families watched space cartoons and dreamed of lunar adventures, the U.S. Army was finalizing a 400-page classified document with a chilling proposal: deploy nuclear weapons on the moon by 1966. Not a research station, a fortress. This wasn't a paranoid fantasy. It was Project Horizon, a fully costed military operation with weapon specifications, construction timelines, and billion-dollar budgets. The question wasn't if America would militarize the moon. The question was which branch would get there first. Because the Air Force had their own plan, and it was even more ambitious. This is how humanity's greatest achievement almost became its most dangerous mistake. To understand why military minds propose nuclear weapons on another world, travel back to October 4th, 1957. The night Sputnik's signal reached Earth, everything changed. That beeping wasn't just technological triumph, it was existential threat. If Soviets could place satellites over American cities, what stopped them from placing weapons? In Pentagon war rooms, strategists stared at maps with dawning horror. Every ocean, mountain range, defensive perimeter humanity ever conceived suddenly meant nothing. The enemy could bypass it all by going up. And if orbital space was vulnerable, what about the moon? The ultimate high ground. 240,000 miles up, rotating slowly enough to observe every military installation, detect every missile launch, track every naval deployment. Nothing could hide. And if observation wasn't enough, that's where Project Horizon came in. March 1959, Army engineers presented Eisenhower their vision, a 12-man lunar outpost operational by December 1966. The base featured modified Claymore mines around its perimeter because the Army genuinely believed Soviet cosmonauts might stage lunar invasions. Picture landmines on the moon, waiting in airless silence for enemies who might never come. Blast patterns calculated for 1/6 gravity. More chilling, the base would carry unguided nuclear missiles, not precision weapons, just raw destructive power aimed at Earth. Launch from the moon, and gravity pulls warheads through the atmosphere at speeds no defense could intercept. Engineers named their fortress Fort Armstrong. They saw themselves as frontier cavalry establishing outposts in hostile territory. Except this territory was 240,000 miles away, where punctured spacesuits meant death in seconds. Temperatures swung from 250 degrees in sunlight to minus 280 in shadow, with no water, no air, no rescue. But the Army wasn't alone. The Air Force developed Project Lunex between 1958 and 1959, making Horizon look modest. While Army envisioned surface fortresses, Air Force planned something sophisticated, a 21-person underground base, buried beneath regolith for radiation protection, designed to survive indefinitely. Think Cheyenne Mountain, the nuclear command bunker carved into Colorado granite, relocated to another celestial body. A subterranean fortress with defensive and offensive capabilities, representing permanent American military presence on another world. The Horizon Lunex debate wasn't just engineering approaches, it was battling for the space program's soul. One branch envisioned fortified Alamos in the sky. The other imagined futuristic underground cities for long-term occupation. Both projects reached Eisenhower's desk within months. Documents revealed something terrifying. Neither planned defense alone. Both discussed Earth strike capabilities. Both outlined strategic dominance. Lunex documents captured the logic brutally. Lunar control equates to Earth control. Whoever holds the moon holds the planet. Two American military branches, supposedly united against Soviet threats, were racing each other to weaponize the moon. They submitted detailed budgets, specifications, launch schedules, operational timelines. These weren't fantasies from overeager officers. These were actionable plans backed by engineering teams, cost analyses, and strategic assessments from experienced defense minds. Inter-service rivalry extended 240,000 miles into space. Both branches were deadly serious. Project Horizon's timeline called for 147 Saturn rocket launches between November 1964 and December 1966. 147 launches in 2 years. NASA launched 13 Saturn pieces during the entire Apollo program. Horizon proposed 10 times that in half the time. Each launch carried cargo to the lunar surface, 220 tons total, prefabricated modules, nuclear reactors, life support, communication equipment, construction machinery, and weapons. Those Claymore mines weren't symbolic. Engineers calculated blast patterns in vacuum, where no atmosphere carries shock waves, no air slows shrapnel. On Earth, Claymore steel balls spread in 60-degree arcs. On the moon, they'd travel perfectly straight until hitting something, potentially miles across lunar surface at lethal velocities. Then nuclear missiles. Unguided ballistics launched toward Earth, allowed to fall. No corrections, no precision. Just aim generally and let lunar escape velocity and Earth's gravity work. Margin of error measured in miles, but with thermonuclear payloads, precision becomes less critical. Once you weaponize the moon, you create an arms race with no exit. Soviets would respond. They couldn't allow exclusive American military control. They'd launch programs, establish bases, deploy weapons. Suddenly the moon becomes not human achievement's symbol, but mutually assured destruction's cosmic trigger. Engineers began having doubts. In classified memos they asked, "Is this the future we want? Are we transforming humanity's greatest adventure into its most dangerous mistake?" Lunex took different approaches with equally disturbing implications. Air Force envisioned nuclear excavation, detonating controlled explosions beneath lunar surface, creating habitable caverns. They'd use excavated regolith as radiation shielding. The underground facility housed 21 personnel across multiple levels: living quarters, command centers, weapons storage, launch facilities. Designed for indefinite occupation, permanent military installation representing American dominance across 250,000 miles. Both projects required reconnaissance orbiters mapping terrain, identifying resources. The peaceful technology we celebrate, robotic probes studying surfaces, analyzing composition, searching for water, was originally conceived for military site selection. Where to build fortresses, find resources, position weapons. As plans reached final stages, as budgets were calculated, timelines refined, engineers solved problems, strategists outlined doctrines, projects moved toward reality, funding available, technology feasible, political will existed. They needed presidential approval, but one man stood between military ambition and weaponized moon. Dwight Eisenhower commanded history's largest military invasion at D-Day. He understood warfare, strategy, high ground importance. Yet when presented with lunar militarization plans, he surprised his generals. He said no. The decision came 1958, as Horizon and Lunex awaited approval. Army wanted their fortress by 1966. Air Force envisioned permanent underground installation, giving America uncontested Earth dominance. Military leaders argued strategic logic was unassailable, funding available, technology feasible. They needed the president's signature. Instead, July 29, 1958, Eisenhower signed the National Aeronautics and Space Act, creating NASA as civilian agency. This wasn't quiet reshuffling. It was deliberate rejection of military space ambitions. Projects effectively canceled before gaining momentum. Plans filed as historical curiosities rather than operational blueprints. Military brass pushed back. They argued keeping exploration civilian during Cold War was naive, dangerous. They warned Eisenhower was surrendering ultimate advantage. They predicted Soviets would militarize while America pursued peaceful exploration. But Eisenhower appointed Keith Glennon as NASA's first administrator. Glennon became unexpected warrior for peaceful exploration, fighting Pentagon turf battles, arguing NASA authority over launches, and planning absorbing military programs and budgets into civilian agency, essentially defunding lunar fortresses by redirecting resources. Behind closed doors, Eisenhower's reasoning was idealistic and strategic. Military experience told him weaponizing guaranteed Soviet response. Every defensive measure becomes offensive threat. Every weapon triggers countermeasures. Arms race already bringing nuclear annihilation's brink would extend where verification was impossible. First strike advantages terrifying. Hope for international treaties limiting space weapons evaporates the moment American missiles install in lunar regolith. Cost measured not just billions, but permanent militarization of humanity's future beyond Earth. Eisenhower gambled peaceful exploration achieves what weapons never could: moral authority, international cooperation. America wins more reaching with open hands instead of clenched fists. First nation reaching another world should represent all humanity, not conquer for military advantage. Between 1959 to 1960, both projects quietly shelved. Official reason: budget constraints, technical challenges. Real reason: political decision pursuing peaceful exploration. Military didn't surrender entirely. Surveillance satellites continued, but Moon preserved as neutral ground. 10 years later, Armstrong stepped onto lunar surface, carrying no weapons, only flag and plaque. "We came in peace for all mankind." Those words weren't inevitable. They resulted from choice. The Moon we know, symbol of achievement and peaceful exploration, exists only because critical 1950s decision. Horizon and Lunex weren't fantasies. They were developed military proposals with budgets, timelines, weapons, engineering solutions. Space race nearly hijacked by Cold War paranoia. 147 launches, 220 tons cargo, Claymore mines, nuclear missiles, all planned, costed, implementation ready. Eisenhower creating civilian NASA didn't just change American policy, changed what Moon means to humanity. Instead of nuclear fortress, it became destination bringing world together. 1967's Outer Space Treaty banned space weapons, codifying what Eisenhower chose. Space remains mankind's province, not superpower battlefield. But that choice isn't permanent. Today, as military satellites multiply, Space Force expands, nations race back with new technologies and old ambitions, we face Eisenhower's decision again. Whether space remains demilitarized or becomes humanity's next battlefield isn't settled history. It's current events. Footprints on Moon are peaceful, not because peace was inevitable, but because someone chose it. In space's vastness, that choice, reaching with open hands instead of clenched fists, might be humanity's most important achievement. The battle for the Moon's soul may not be over. It may have only just begun. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
5 nuclear reactors sit on the surface of the Moon right now. Not reactors in the traditional sense, but plutonium-238 power sources generating heat and electricity in the lunar vacuum. They have been there for over 50 years. Most people assume they were built specifically for Apollo, custom engineering for a singular mission. That assumption is wrong. The SNAP-27 radioisotope, thermoelectric generator that powered every Apollo lunar surface experiments package from Mission 12 onwards, was not a Moon program invention. It was a dual-use technology, developed in parallel with the Navy's most classified surveillance systems. The same power units that kept seismometers running in the Sea of Tranquility were keeping undersea listening arrays operational in the Atlantic Trench. The same thermocouples converting plutonium decay heat into electricity on Oceanus Procellarum were doing identical work in orbit, powering transit navigation satellites that guided ballistic missile submarines to their launch positions. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster. We focus on what was built, why it mattered, and where it really led. Now, back to the story. The Moon was not just a scientific laboratory, it was a proving ground. A test site for nuclear power systems that would become the backbone of American strategic surveillance for the next half-century. And almost no one knew it. To understand how this happened, we need to go back to 1959, to a program most people have never heard of. SNAP stands for Systems for Nuclear Auxiliary Power. It was an Atomic Energy Commission initiative to develop compact nuclear power sources for applications where solar panels would not work and batteries would not last. Deep space, deep ocean, high latitude, anywhere the sun was unreliable or absent. The program began with SNAP-1, a small reactor designed to produce 500 watts of electrical power. But reactors are complex. They require cooling systems, control rods, shielding. They have moving parts that can fail. For long-duration missions in hostile environments, engineers wanted something simpler. Something with no moving parts. Something that would work for decades without maintenance. That led them to radioisotope thermoelectric generators. The concept is elegant in its simplicity. Take a chunk of radioactive material that generates heat as it decays. Surround it with thermocouples, devices that convert temperature differences directly into electricity. No turbines, no coolant loops, no control systems. Just physics, working continuously for as long as the isotope continues to decay. Plutonium. 238 became the isotope of choice, not to be confused with plutonium-239, the weapons-grade material. Plutonium-238 is not fissile. It cannot sustain a chain reaction. It cannot be used in a bomb. But it has a half-life of 87.7 years and generates tremendous heat through alpha decay. 1 kilogram of plutonium-238 produces 560 watts of thermal power, continuously, for decades. The Navy saw the potential immediately. In 1959, the transit program was developing the world's first satellite navigation system. These satellites needed to operate in polar orbits, spending significant time in Earth's shadow, where solar panels would be useless. They needed power sources that would work regardless of sun angle, regardless of orbital position, for years at a time. SNAP-3 became the first radioisotope generator to fly in space, launching aboard Transit 4A in June 1961. It produced 2.7 watts of electrical power from a plutonium-238 fuel capsule the size of a coffee can. But the Navy's interest went far beyond navigation satellites. In the early 1960s, the United States was deploying an extensive network of undersea surveillance systems designed to track Soviet submarines. The sound surveillance system, known as SOSUS, consisted of arrays of hydrophones placed on the ocean floor at strategic choke points. These arrays needed power. Lots of it, are for years. In locations where running cables was impossible and servicing was impractical. The Atomic Energy Commission and the Navy began developing SNAP family units specifically for undersea and remote applications. These systems were highly classified. Their locations were classified. Their capabilities were classified. Even their existence was barely acknowledged. But they were being built, tested, and deployed throughout the 1960s, in parallel with the space program. Then Apollo happened. And suddenly, NASA needed exactly the same thing the Navy needed. Long-duration power in a hostile environment with no maintenance. The early Apollo missions, 11 through 14, carried scientific experiments to the lunar surface. But these experiments were limited. They ran on batteries that lasted hours, maybe days. If NASA wanted to conduct long-term studies of the moon, if they wanted to measure seismic activity and solar wind and magnetic fields over months and years, they needed a different power source. In 1965, NASA and the AEC began formal collaboration on a lunar RTG. The program was designated SNAP-27. But this was not a new design. It was an adaptation of existing SNAP technology, modified for lunar conditions. The fuel capsule, the thermocouples, the basic architecture, all of it drew directly from systems already under development for Navy applications. The SNAP-27 design is deceptively simple. At its core is a plutonium-238 fuel capsule containing approximately 3.8 kilograms of plutonium oxide. This capsule generates 1,480 watts of thermal power. Surrounding the capsule are hundreds of lead telluride thermocouples arranged in a cylindrical array. These thermocouples convert the temperature difference between the hot fuel capsule and the cold outer case into electricity. The system produces 73 watts of electrical power at 16 volts DC. Efficiency is only about 5%, but efficiency does not matter when your fuel lasts for decades. The outer case is designed to radiate excess heat into space. On the moon, with no atmosphere to convect heat away, radiation is the only cooling mechanism. The case is covered with aluminum fins to maximize surface area. During lunar day, with surface temperatures reaching 120 degrees Celsius, the RTG runs hot. During lunar night, when temperatures drop to minus 170 degrees Celsius, it runs cooler. But it keeps running. The thermocouples do not care about ambient temperature. They only care about the temperature difference between the hot and cold junctions. The most critical component is the fuel capsule itself. Plutonium-238 is intensely radioactive. The alpha particles it emits are stopped by a sheet of paper, but if the material is dispersed and inhaled, it is catastrophically toxic. The fuel capsule had to be designed to survive any credible accident scenario. Launch pad explosion, re-entry from orbit, impact with the lunar surface at terminal velocity. The capsule uses multiple containment layers. The plutonium oxide fuel is pressed into a ceramic form and sealed inside refractory metal capsules. Those sit inside high-strength alloy members. The assembly is protected by graphite impact shells. Yet the entire package is designed to remain intact at temperatures exceeding 2,000 degrees Celsius. This level of engineering was not developed for Apollo. It was developed for systems that might end up on the ocean floor, or re-entering the atmosphere uncontrolled, or sitting in a foreign port after a satellite failure. The Navy needed fuel capsules that could survive worst-case scenarios without releasing plutonium. NASA inherited that technology. The SNAP-27 flew for the first time on Apollo 12 in November 1969. The mission carried the first Apollo Lunar Surface Experiments package, known as ALSEP. The package included a seismometer, a magnetometer, a solar wind spectrometer, and an instrument to measure the lunar atmosphere. All of it powered by the RTG, sitting about 100 meters from the lunar module to avoid thermal interference. Your astronaut Alan Bean removed the fuel capsule from its cask in the lunar module and carried it to the RTG, inserting it manually. The procedure was straightforward but carried obvious risk. Bean was handling a fuel element generating 1,480 watts of heat, hot enough to cause severe burns on contact. He used a handling tool, but the operation required precision. Once the capsule was seated, the RTG began generating power immediately. No startup sequence, no warm-up period, just physics. The ALSEP operated for nearly 8 years, transmitting data continuously until September 1977, when NASA shut down the entire ALSEP network for budgetary reasons. The instruments were still functioning. The RTG was still producing adequate power. But the ground stations and data processing were expensive, and other priorities took precedence. Or the experiments went silent, but the RTG kept running. It is still running today, producing about 50 watts, roughly 70% of its original output after 5 decades of continuous operation. Apollo 13 was supposed to carry the second SNAP-27, but the mission never landed. The RTG fuel capsule re-entered Earth's atmosphere inside the lunar module Aquarius, which burned up over the South Pacific. The fuel capsule, with its multiple containment layers, survived intact and sank to the ocean floor near the Tonga Trench. It sits there still in roughly 6,000 meters of water, slowly decaying, contained and inert. Recovery was considered and rejected. The capsule posed no environmental threat, and retrieval would have been extraordinarily difficult. Easier to leave it. Apollo 14 through 17 each carried a SNAP-27, while 5 units total reached the lunar surface. Each one powered an ALSEP station. Each one operated for years. The longest-running unit, from Apollo 17, transmitted data until the network shut down in 1977. All 5 are still on the moon, still generating heat, still producing electricity that no one is using. They will continue operating at diminishing output for another century at least. But the moon was never the primary application. It was a test bed, a demonstration environment, a place to prove the technology worked under the most extreme conditions imaginable. Because while NASA was landing RTGs on the moon, the Navy was deploying SNAP family technology for classified applications around the world. The Transit Navigation Satellite program expanded throughout the 1960s and 1970s. Later, transit satellites used SNAP 9A generators, on larger units producing 25 watts each. In 1964, Transit 5B-N3 failed to reach orbit. The satellite re-entered over the Indian Ocean, and the SNAP 9A fuel capsule burned up, dispersing 950 grams of plutonium-238 into the upper atmosphere. The contamination was detectable worldwide. The incident led to improved fuel capsule designs, the same multi-layer containment systems that flew on Apollo. The SOSUS network expanded as well. SNAP family technology was developed in parallel for undersea and remote surveillance applications, systems that remain classified to this day. Some of these programs are still operating today, more than 50 years after initial deployment. Their exact nature and locations are not public information. But the technology that proved itself on the moon found its way into strategic systems worldwide. And the dual-use nature of the program was never explicitly hidden, but it was never advertised either. NASA presented the SNAP-27 as a lunar technology, purpose-built for Apollo. The Atomic Energy Commission and the Navy said very little about their own applications. The public saw RTGs as a space technology, exotic and futuristic. Few realized the same basic technology was being developed for the deep ocean, for classified satellite constellations, for monitoring stations at remote locations around the world. This was not a conspiracy. It was operational security. The Navy did not want adversaries knowing where their undersea listening posts were located or how they were powered. The AEC did not want attention drawn to the production and deployment of kilogram quantities of plutonium-238. Apollo provided perfect cover, but public attention focused on the moon, on the astronauts, on the scientific experiments. The power source was a technical detail, interesting but secondary. Meanwhile, the same technology was being integrated into strategic surveillance systems that would shape the Cold War. The long-term performance data from the lunar RTGs was invaluable. Engineers knew the theoretical lifespan of thermocouples and fuel capsules, but theory and reality often diverge. The moon provided a perfect test environment. Hard vacuum, extreme temperature swings, no maintenance, no human intervention. If an RTG could survive and operate on the moon for a decade, it could survive anywhere. The data from ALSEP fed directly back into Navy and AEC programs, validating designs and informing future systems. By the mid-1970s, RTG technology was mature and proven. The Voyager program, launching in 1977, carried 3 RTGs per spacecraft, SNAP 19 units producing a combined 450 watts. Those RTGs are still operating today, 47 years later, powering spacecraft in interstellar space. The Cassini mission to Saturn carried 3 larger units, producing 870 watts at launch. The Curiosity and Perseverance Mars rovers each carry a multi-mission RTG, producing 110 watts. Every deep space mission beyond the asteroid belt has used RTG power. The technology is indispensable, but the military applications remain the most significant. Modern reconnaissance satellites use RTGs when solar power is insufficient. Undersea surveillance systems continue to rely on them. Remote monitoring stations in polar regions use them. The technology that powered experiments on the moon became the foundation for strategic capabilities that persist today. There is a melancholy to this story. The SNAP-27 units on the moon are monuments to a particular moment in history when space exploration and military technology were inseparably intertwined. They sit in the lunar dust, still warm, still generating electricity, serving no purpose. The experiments they powered were shut down for budget reasons, not technical ones. The science was good. The instruments worked. But priorities shifted. Funding dried up, and the decision was made to stop listening. Those RTGs could still be powering experiments today. With modern electronics requiring far less power, a single Snap 27 could run an entire suite of instruments. But there are no instruments. There are no receivers. There is no mission. Just 5 nuclear batteries slowly cooling, waiting for someone to return. The technology itself represents a path not taken. RTGs offer capabilities that no other power source can match for certain applications. But they require plutonium-238, and plutonium-238 production stopped in the United States in 1988. For nearly 3 decades, NASA relied on stockpiled material and purchases from Russia. Domestic production only resumed in 2015 at a fraction of Cold War levels. Current production is roughly 300 grams per year. A single Snap 27 used 3,800 grams. The infrastructure to produce RTGs at scale no longer exists. This is a recurring pattern in the history of space technology. Capabilities are developed, proven, deployed, and then allowed to atrophy. The institutional knowledge fades. The supply chains disappear, and the workforce retires. What was routine becomes difficult, then impossible. We can still build RTGs, but not quickly, not cheaply, and not in large numbers. The systems that powered Apollo and the Navy's surveillance networks were products of a massive industrial base that no longer exists. The Snap 27 units on the Moon will outlast the flags and footprints. Fabric and boot prints will eventually be destroyed by micrometeorite bombardment and ultraviolet radiation. But the RTGs are solid metal and ceramic, built to survive re-entry and impact. They will sit there, intact and functional, for centuries, long after the last person who worked on them has died, long after the political circumstances that created them have been forgotten. They will remain, generating heat, a testament to what was briefly possible. When future missions return to the Apollo sites, those RTGs will still be there, still warm to the touch, still producing a trickle of electricity. They are perhaps the most durable artifacts of the space age, not the rockets, which were destroyed in flight, not the spacecraft, which are fragile and corroding, but the nuclear batteries built to last, doing exactly what they were designed to do, decades after anyone stopped caring. There is a broader lesson here about dual-use technology and the relationship between civilian and military programs. Apollo was sold to the public as peaceful exploration, and it was. But the technologies it developed and proved had immediate military applications. The RTGs are the most obvious example, but the pattern extends to rockets, guidance systems, communications, material science. Or the line between exploration and strategic capability has always been blurred. This is not a criticism. It is an observation. Large-scale technology development requires resources and political will. In the 1960s, both were available because of Cold War competition. Apollo and the Navy's surveillance programs were funded by the same government, driven by the same geopolitical imperatives. The technologies they developed served both purposes. That is simply how it worked. But it means the history we tell about these programs is incomplete. The public narrative of Apollo focuses on exploration, science, human achievement. That narrative is true but partial. The shadow history includes strategic surveillance, nuclear power systems, and military applications that were classified for decades. Both histories are real. Both matter. And understanding the full story requires looking at both. The Snap 27 is a perfect emblem of this duality. It is a scientific instrument, powering experiments that expanded human knowledge of the Moon. It is also a military technology, proven in the most demanding environment imaginable, then deployed in classified systems worldwide. It is both things simultaneously. That is what makes it significant. 5 nuclear batteries sit on the moon, still running, serving no purpose, waiting for a future that may never come. They are the most enduring legacy of Apollo, more permanent than memory, more reliable than politics. They will be there long after we are gone, generating heat in the vacuum, monuments to a moment when anything seemed possible and the future was being built in parallel. One version for the public, another in the shadows. Both real, both necessary, both now part of history. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
Watch this rocket land. Now watch it again. The date on the screen reads August 18th, 1993, 22 years before SpaceX made headlines with the same technology. A 40-foot metal cone rises into the New Mexico sky on pillars of flame, stops midair like it's forgotten the laws of physics, slides sideways like a helicopter, then descends and touches down on 4 spindly legs. No parachutes. No ocean splashdown, no army of recovery crews. Just a rocket landing like it's the most natural thing in the world. This was the DCX, the Delta Clipper experimental. And what you just witnessed wasn't a special effect. It was real hardware proving that everything NASA believed about rockets was wrong. Here's the part that should make you angry. While NASA was hemorrhaging $196 billion on the Space Shuttle program, a small team at McDonnell Douglas built and flew this machine for under $60 million. $60 million, that's less than what some government agencies spend on office furniture. And with that shoestring budget, they proved the core concept of reusable rocketry in just 8 flights. So why have you never heard of the DCX? Because 3 years after that first triumph, a single missing part, a 25-cent cotter pin, would destroy not just this rocket, but the entire future it represented. This is the story of the spacecraft that could have changed everything, and the bureaucratic indifference that let it burn. The vision began decades earlier, in the mind of a man named Philip Bono. Throughout the 1960s, while NASA was building expendable rockets to reach the moon, Bono was sketching something different, single-stage to orbit vehicles that would operate like airplanes. Take off, land, refuel, repeat. His designs gathered dust in aerospace archives, dismissed as impractical fantasy. The math worked, the physics worked, but the will to build them didn't exist until Max Hunter came along. Hunter was a pragmatic McDonnell Douglas engineer who looked at the space shuttle with its army of technicians, its months-long refurbishment cycles, its expendable external tank, and asked a heretical question: why can't rockets work like airplanes? He called the DCX the most exciting project of my career, proving that rockets could be as reliable as airplanes. That statement wasn't just optimism, it was a declaration of war against decades of aerospace orthodoxy. The orthodoxy said rockets must be complex, expensive, and expendable. The orthodoxy said vertical landing was too difficult, too risky, too impractical. The orthodoxy was backed by billions of dollars in existing programs and thousands of engineers whose careers depended on maintaining the status quo. Hunter and his team were about to prove the orthodoxy was fundamentally wrong. But they'd have to do it without NASA's help. In fact, they'd have to do it despite NASA's skepticism. The funding came from an unlikely source: the Strategic Defense Initiative Organization. Yes, the Star Wars missile defense program. At the tail end of the Cold War, General Daniel Graham saw rapid, reusable space operations as a strategic asset. The ability to launch quickly, land, refuel, and launch again wasn't just efficient, it was militarily valuable. So he handed Hunter's team a microscopic budget and essentially said, "Prove it works." The design philosophy was radical in its simplicity. 4RL-10A-5 liquid hydrogen and oxygen engines, already proven reliable in other applications, producing 60,000 pounds of thrust total. commercial off-the-shelf avionics, the same kind of systems you'd find in passenger jets. An automated flight control system that could land the vehicle without human intervention. No exotic materials, no billion-dollar custom components, just smart engineering using existing technology. Think about what this meant. While NASA's space shuttle required 3 main engines, 2 solid rocket boosters, an expendable external tank, and thousands of heat-resistant tiles that had to be individually inspected after every flight, the DCX was essentially a flying fuel tank with 4 engines and a computer. It was the engineering equivalent of Occam's razor. The simplest solution is usually the right one. But simple doesn't mean easy. Hunter's team was attempting something no one had successfully demonstrated. A rocket that could take off vertically, hover in midair, translate sideways, and land vertically, all autonomously. The automated flight control system would have to make thousands of micro-adjustments per second, gimbaling the engines and throttling them precisely to maintain stability. One miscalculation, one sensor failure, one software bug, and the vehicle would become a very expensive firework. And behind the technical challenge lurked a more insidious threat: institutional resistance. NASA wasn't just skeptical of the DCX, they were actively dismissive. Internal memos from the era reveal a culture that viewed the project as a threat rather than an opportunity. This wasn't just "not invented here" syndrome. It was something darker. The recognition that if this small team succeeded where NASA's massive programs had failed, it would raise uncomfortable questions about how the agency had been spending billions of taxpayer dollars. But proving the skeptics wrong would require more than clever engineering. It would require the vehicle to actually fly. And that's where things got dangerous. August 18th, 1993. The New Mexico desert shimmers in the heat as the DCX sits on its launch pad, looking less like a rocket and more like an oversized traffic cone. The McDonnell Douglas team has spent months preparing for this moment, knowing that a single failure will give NASA all the ammunition they need to kill the program. The countdown reaches 0. The RL-10 engines ignite, and the DCX rises on 4 pillars of flame. But this isn't like watching a normal rocket launch, where the vehicle accelerates skyward and disappears. The DCX climbs slowly, deliberately, then stops. It hovers. The automated flight control system is working exactly as designed, making thousands of tiny adjustments to keep the vehicle stable. Then it does something no rocket had ever done before. It moves sideways, translating horizontally while maintaining altitude, demonstrating the kind of maneuverability you'd expect from a helicopter, not a rocket. Then it descends, engines throttling precisely, and touches down on its 4 landing legs. The entire flight lasts just over 1 minute. But in that minute, everything changed. Pete Conrad was there that day. The Apollo 12 astronaut who had walked on the moon, who had piloted the lunar module to the surface of another world, stood in the New Mexico desert and watched this cone-shaped rocket land. His reaction, describing it as seeing the future unfold. Think about that for a moment. A man who had commanded some of the most sophisticated flying machines ever built, who had accomplished one of humanity's greatest technical achievements, was awestruck by watching this prototype touchdown. Because he understood what it meant. This wasn't just another test vehicle. This was proof that the entire paradigm of spaceflight could change. Over the next 2 years, the DCX would fly 7 more times, each flight pushing the envelope further. The vehicle reached altitudes over 10,000 feet. It hit speeds of 230 miles per hour, not orbital velocities, but that wasn't the point. The point was demonstrating that vertical takeoff and landing wasn't just possible, it was practical. Each successful flight was a middle finger to the skeptics who had said it couldn't be done. But the most impressive number wasn't how high it flew or how fast it went. The most impressive number was 26. The DCX team demonstrated rapid turnaround capabilities. They launched the vehicle, watched it climb and land successfully, then turned around and did it again in 26 hours. Not 26 weeks, not 26 days, 26 hours from landing to launch. Let that sink in. The space shuttle required months of refurbishment between flights, pulling heat tiles, inspecting thousands of components, essentially rebuilding parts of the vehicle. Here was Hunter's team rolling a rocket back to the pad, topping off the tanks, running through checks, and lighting the engines again before the desert sand had even cooled from the previous landing. They were operating a rocket like an aircraft. And it wasn't a fluke. They kept proving it, flight after flight. The economics were even more staggering. Each DCX flight cost approximately $500,000. Each space shuttle launch, over $1 billion. The entire DCX program, design, construction, and all 8 test flights, came in under $60 million. To put that in perspective, if the DCX program was a single grain of sand, the Space Shuttle program was a dump truck full of concrete. McDonnell Douglas was proving that the astronomical costs everyone accepted as inevitable for spaceflight were actually the result of throwing away perfectly good hardware after every mission. The data was undeniable. The technology worked. The operational concept worked. The economics worked. Hunter's team had done the impossible. They had proven that decades of aerospace orthodoxy was wrong. But success in the desert meant nothing without NASA's commitment. And NASA was watching with a mixture of fascination and dread. Because if the DCX was right, it meant NASA's entire approach had been wrong. It meant the billions poured into the space shuttle, the thousands of engineers dedicated to maintaining it, the political constituencies built around it. All of it was based on a false premise. So in 1995, NASA did something that seemed like validation, but felt like a threat. They took over the program. The DCX was transferred to NASA and rechristened the DCXA. The A stood for advanced. The vehicle would be upgraded with cutting-edge composite tanks and Russian aerospace technology, pushing the performance envelope even further. On paper, it looked like the program was graduating to the big leagues. In reality, it was about to enter a bureaucratic culture that had a very different definition of success. The DCX had proven its concept under the scrappy, move fast and break things culture of the Strategic Defense Initiative. Now it would be tested under NASA's risk-averse, procedure-heavy management. The original McDonnell Douglas team, the engineers who had achieved 26-hour turnarounds, watched nervously as their creation passed into new hands. And on July 31st, 1996, their worst fears would be realized. July 31st, 1996. The DCXA, now wearing its NASA badge and sporting advanced composite tanks imported from Russian aerospace technology, sits on the launch pad in New Mexico. This is its 4th flight under NASA management. The previous 3 had gone well, demonstrating even more aggressive flight profiles than the original DCX. Today's mission: climb to over 2,000 feet, execute a series of maneuvers, and land. The countdown reaches 0. The RL-10 engines ignite. The DCXA rises smoothly, its automated flight control system working flawlessly. The vehicle climbs to 3,140 feet, higher than it had ever flown before. At the apex, it performs its programmed maneuvers perfectly. Then it begins its descent, engines throttling precisely, the computer making thousands of micro adjustments to keep it stable. Everything is working exactly as designed. The team watches the telemetry. All systems nominal. The vehicle descends through 100 feet, 50 feet, 20 feet. The landing legs should be deploying now. 3 legs extend. 1 doesn't. The DCXA touches down on 3 legs, teeters for a heartbeat, then tips over. In slow motion, the way catastrophes always seem to unfold, the vehicle crumples against the concrete pad. The composite fuel tanks rupture. Liquid hydrogen and liquid oxygen mix. The fireball consumes years of groundbreaking work in seconds. The investigation found the cause immediately: a missing cotter pin. Let me show you what a cotter pin looks like. It's a small, bent piece of metal, roughly the size of a paperclip. Its job is simple. It slides through a bolt to keep it from unscrewing. Cost: 25 cents. You can buy them at any hardware store. This particular cotter pin was supposed to lock a hydraulic line in place. Without it, the hydraulic fluid leaked out during flight. When the landing gear deployment command came, there was no pressure to extend that one critical leg. A $250 part. A single missed checkbox on a pre-flight inspection. One tiny piece of hardware that should have been installed but wasn't. The engineers who had achieved 26-hour turnarounds, who had proven that rockets could land like airplanes, watched their vehicle burn because someone missed a step. But here's what makes this story truly infuriating. The real failure wasn't mechanical, it was institutional. Under the original McDonnell Douglas management, that pre-flight inspection would never have been skipped. The team that had operated the DCX for 8 successful flights had developed procedures honed through rapid iteration. They knew every bolt, every line, every critical component. When NASA took over, those procedures entered a bureaucratic system where accountability was diffuse and innovation was expendable. The missing cotter pin wasn't just a mechanical oversight. It was a symptom of a culture that had never truly wanted this technology to succeed. NASA had the data. They had the hardware. They had incontrovertible proof that reusable vertical landing rockets worked. The DCX had compiled 8 successful flights. The DCX-A had completed 3 more ambitious test campaigns. The technology was proven. The operational concept was validated. And NASA chose not to rebuild. They chose to move on. Instead, the agency doubled down on the X-33, a vastly more complex single-stage-to-orbit vehicle that would consume over $1.3 billion before its own cancellation in 2001, without ever flying. The X-33 would fail for exactly the reasons the DCX team had warned about. Trying to achieve orbit in a single stage required exotic materials and technologies that weren't ready. The DCX approach, prove the basics first, scale up gradually, was abandoned in favor of an all-or-nothing gamble that achieved nothing. Engineers from the DCX team described the atmosphere after the crash as one of intense frustration at lost opportunities. They knew that a simple checklist failure had destroyed years of groundbreaking work. They knew the technology was sound. They knew that rebuilding would have cost a fraction of what NASA was about to pour into the X-33's doomed development. And they knew that no one in power was listening. Years later, Charles Bolden, who would become NASA administrator, reflected, "DCX showed us what was possible, even if it was ahead of its time." It's the kind of thing people say when they're trying to soften a catastrophic institutional failure. Because the DCX wasn't ahead of its time, it was exactly on time. What it was ahead of was NASA's willingness to embrace a technology that hadn't been invented within the agency's own walls. A $250 part, 19 years of delay. And the question that still haunts the engineers who were there: what world would we be living in if that pin had been installed? Imagine an alternate timeline. It's the year 2000, and reusable rockets are routine. The DCX's descendants are launching satellites every week, their 26-hour turnarounds making space access as regular as commercial air travel. The cost per kilogram to orbit has dropped by an order of magnitude. The International Space Station was built faster and cheaper because launch costs weren't prohibitive. Mars missions are being planned not as distant dreams, but as achievable goals within the decade. That timeline was possible. The DCX proved it. The technology worked in 1993. The engineering was sound. The operational concept was validated. What failed was the system meant to nurture innovation. Today, when we watch SpaceX Falcon 9 boosters land on drone ships, when we see Blue Origin's New Shepard touch down in the desert, we're not witnessing the birth of reusable spaceflight. We're witnessing its resurrection. Elon Musk has explicitly cited the DCX as a direct inspiration for the Falcon 9. Blue Origin's New Shepard adopted its core principles: vertical landing, rapid turnaround, autonomous flight control. Every reusable rocket flying today traces its conceptual lineage back to that cone-shaped prototype in the New Mexico desert. The DCX proved it could be done in 1993. The world just wasn't ready to listen until SpaceX landed a Falcon 9 first stage on a barge in 2015, 22 years later. 22 years. Billions of dollars. Countless lost opportunities. Missions not flown. Discoveries not made. Scientific instruments that could have been launched but weren't. All because NASA looked at a working prototype and decided the future could wait. The real tragedy isn't the crashed rocket. It's the 2 decades of lost progress. It's the realization that bureaucratic inertia valued protecting the status quo over embracing transformation. It's the knowledge that we could have had routine, affordable spaceflight by the turn of the millennium, and we chose not to because the technology threatened existing power structures. Somewhere in a New Mexico desert, there's a concrete pad where the future once landed and took off again in 26 hours. It took us 20 years to return to that spot, not physically, but technologically. The DCX didn't fail. We failed it. And every time you watch a Falcon 9 land, you're watching the ghost of a 1990s rocket that tried to warn us. The future doesn't wait for permission. It just waits. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.